So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, your phone is connected to a Wi-Fi network. And that connection, that invisible thread tying your device to the internet, depends on a number that doesn't exist. Literally, the entire mathematical backbone of wireless communication runs through something called the square root of -1, a number that, for centuries, mathematicians insisted could not be real, could not mean anything, could not have any possible use. They called it imaginary, which is the word we still use for it, and they meant it as an insult. And yet, here we are, 400 years later, and that impossible number is woven into the signal processing that keeps your phone alive, the electrical engineering that powers the grid, the quantum mechanics that explains why matter exists at all. And now, right now, in laboratories in New York, in Zurich, in Shanghai, in the suburbs of Sydney, engineers are building a new kind of computer, a machine so fundamentally different from anything we've ever constructed that it makes a modern laptop look like an abacus. And this machine, this quantum computer, the thing that governments and corporations are spending billions of dollars to build, runs entirely, from its most basic operations to its most powerful algorithms, on that same impossible mathematics. Complex numbers, matrices, vector spaces, linear algebra. The whole apparatus of abstract math that generations of students have struggled through, wondering what it could possibly be good for, turns out to be the operating language of the most powerful computational device ever conceived. And that's what I want to talk about tonight. Because the story of how we got here, how an insult became a foundation, how a mathematical fiction became the blueprint for a machine that could reshape civilization, that story is one of the strangest and most beautiful threads in all of human thought. And it stretches across 5 centuries, from a gambling Italian mathematician in the 1500s who stumbled onto a number that made no sense, to a 25-year-old physicist on a treeless island in the North Sea who accidentally reinvented matrix multiplication without knowing it existed, all the way to a quiet office in Bell Labs in New Jersey in 1994, where a man named Peter Shor wrote down an algorithm that could, in principle, crack the encryption protecting every bank, every military, every government on Earth. All of it connected, all of it running through the same vein of abstract, supposedly useless mathematics. So here are the questions I want to sit with tonight. How did numbers that don't exist become the language of reality? Why does the universe, at its deepest level, speak in a mathematics that humans invented as a kind of workaround for equations they couldn't solve? What happens when you build a computer that speaks that language natively, not translating from the language of switches and circuits, but thinking in the native tongue of atoms? And what does it mean that the encryption protecting your bank account right now, your medical records, your private messages, everything you consider secure, rests on a single mathematical assumption that a quantum computer could shatter? And maybe the biggest question of all, one that runs beneath everything we'll talk about tonight, is this: is mathematics something we invent or something we discover? Because the answer to that question shapes how you hear this entire story. If math is a human invention, then the fact that quantum computers work is an almost absurd coincidence, like finding out that a poem you wrote as a teenager perfectly describes the internal structure of a star. If math is something we discover, something that was always there, waiting in the fabric of things, then the story is even stranger, because it means that when Gerolamo Cardano reluctantly wrote down the square root of -1 in 1545, he wasn't inventing a trick. He was picking up a thread that leads, in an unbroken line, to the most advanced technology our species has ever attempted to build. We're going to follow that thread tonight, slowly, from the very beginning. And if you drift off somewhere along the way, that's fine. The math will still be here in the morning, it always has been. Let's start in Italy, because that's where this story begins, and it begins with a fight. Not a metaphorical fight, an actual public intellectual combat, conducted before a live audience, with money on the line and reputations at stake. This was how mathematics worked in 16th century Italy. If you were a mathematician, your livelihood depended on your ability to solve problems that other mathematicians could not. Universities hired you based on public contests. You would challenge a rival. Each of you would submit a list of problems to the other, and whoever solved more of them won the position, the salary, the prestige. It was mathematics as blood sport, and the weapons of choice were equations. Now, to set the scene properly, you need to understand where European mathematics stood around 1500. Quadratic equations, the ones where the highest power of the unknown is 2, like x squared plus 5x equals 14, those had been solvable for centuries. Scholars in the Islamic world, particularly al-Khwarizmi in 9th century Baghdad, had developed systematic methods for them. The word algebra itself comes from the title of al-Khwarizmi's book, Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, which roughly translates to the compendious book on calculation by completion and balancing. And those methods had made their way to Europe through translations, through trade, through the slow diffusion of knowledge across the Mediterranean. But cubic equations, the ones where the highest power is 3, like x cubed plus 6x equals 20, those were a different beast entirely. Nobody had a general method for solving them, and finding one became the great mathematical prize of the era. In the early 1500s, a professor at the University of Bologna named Scipione del Ferro quietly found a method for solving a particular type of cubic equation, the so-called depressed cubic, where there's no x squared term. He kept it secret. And that decision, the decision to hoard the solution rather than publish it, tells you everything about the culture of mathematics at the time. Knowledge was currency. You didn't share it. You banked it for the next contest. Del Ferro died in 1526, but before he died, he passed his secret on to a student named Antonio Fior. And Fior, who was apparently not the sharpest mind in Bologna, decided to use his inherited weapon to challenge a much more formidable mathematician, Niccolò Fontana, better known as Tartaglia, which means the stammerer. Tartaglia had been slashed across the face by a French soldier as a boy during the sack of Brescia, and the wound had left him with a severe speech impediment. He was largely self-taught, brilliant, combative, and deeply protective of his ideas. Fior challenged Tartaglia in 1535, each submitting 30 problems to the other. Fior's problems were all cubics of the type he knew how to solve. Tartaglia's problems were a mix. And here's where the drama begins. Tartaglia did not, at the start, know how to solve cubic equations. But under the pressure of the contest, with his livelihood and reputation on the line, he figured it out. In a burst of frantic work in the days before the deadline, he found a general method. He solved all 30 of Fior's problems. Fior solved none of Tartaglia's. Now enter Gerolamo Cardano. Cardano was a physician, astrologer, gambler, philosopher, and mathematician in Milan, one of the most colorful and brilliant minds of the Italian Renaissance. He heard about Tartaglia's triumph and wanted to know the method. He invited Tartaglia to Milan, flattered him, wined him, dined him, and eventually persuaded him to reveal the secret, but only under an oath of secrecy. Tartaglia made Cardano swear never to publish it. Cardano swore. And then, over the next several years, Cardano and his student Lodovico Ferrari extended Tartaglia's method, solved the general cubic, solved the quartic, the fourth-degree equation, and transformed the entire landscape of algebra. And in 1545, Cardano published it all in a book called Ars Magna, the great art. He credited Tartaglia with the original insight, but he published it nonetheless. Tartaglia was furious. The resulting feud, conducted through public letters, pamphlets, and at least one disastrous public debate, became one of the most famous disputes in the history of mathematics. But here's the part that matters for us, the part that connects a 16th century mathematical brawl to a quantum computer humming away in a laboratory in 2026. While working through the solutions to cubic equations, Cardano ran into a problem. Some of the intermediate steps in his formulas required him to take the square root of a negative number, and that should have been impossible. The square of any positive number is positive. The square of any negative number is also positive. So what could it possibly mean to take the square root of a negative number? There is no number on the number line, no quantity you can point to, that when multiplied by itself gives you a negative result. Cardano didn't like it. He called these numbers sophistic and described working with them as being as subtle as it is useless. He acknowledged that his formulas produced them, but he treated them as a kind of temporary embarrassment, something you pass through on the way to a real answer, like walking through a muddy field to get to a clean road on the other side. The intermediate steps were ugly and senseless, but if you held your nose and kept calculating, you came out the other side with a perfectly real, perfectly sensible solution. And that's worth pausing on, because Cardano had stumbled onto something profound, and he almost grasped it. The square root of -1 wasn't a number in any sense he understood. It didn't measure anything. You couldn't count with it. You couldn't find it on a ruler or a scale. And yet it worked. The formulas that used it produced correct answers. The universe, or at least the mathematics describing it, seemed to need this impossible object as a kind of passageway, an underground tunnel connecting one real answer to another. But Cardano was too disturbed by the idea to pursue it further. He noted it, complained about it, and moved on. It would take another mathematician, a generation later, to take the next step. And that mathematician's name was Raphael Bombelli. Bombelli was an engineer from Bologna, practical-minded, resourceful, and unusually comfortable with uncomfortable mathematics. Where Cardano had recoiled from the square root of -1, Bombelli leaned in. In his 1572 book, L'Algebra, Bombelli did something radical. He sat down and worked out the rules of arithmetic for these impossible numbers. If you have the square root of -1, which he called più di meno, roughly plus of minus, what happens when you add it to another such number? What happens when you multiply two of them together? What about multiplying the square root of -1 by itself? Well, that last one was clear enough. The square root of -1 multiplied by itself gives you -1. That's what a square root means. But Bombelli went further. He showed that you could treat these numbers as a new kind of arithmetic with consistent rules, and that those rules let you navigate through Cardano's ugly intermediate steps to reach the correct real solutions of cubic equations. The impossible numbers weren't errors, they were tools. And here's the key insight, the one that Bombelli glimpsed and that would take another 200 years to fully develop. These numbers lived somewhere. They had a structure. They obeyed rules. They just didn't live on the ordinary number line. They were, in a sense, perpendicular to it, sticking out into a dimension that ordinary counting couldn't reach. Bombelli didn't have the language to say this yet. Nobody did. But the implication was already there, buried in the arithmetic. The number line, that straight, clean, one-dimensional ruler stretching from -infinity to +infinity, was not the whole picture. There was more. And the more that was there would turn out to be essential, not just for solving cubic equations, but for understanding the fundamental nature of physical reality. But we're getting ahead of ourselves. For now, in 1572, Bombelli had done something remarkable. He'd taken a mathematical ghost, a number that everyone agreed couldn't exist, and given it a grammar. Rules of addition, subtraction, multiplication. A consistent, reliable, boring little arithmetic. And the fact that it was boring was actually the point. Boring means reliable. Boring means you can build on it. The most exciting breakthroughs in mathematics often arrive wearing very dull clothing. The mathematical world moved on. For the next century and a half, imaginary numbers, as they would eventually be called, lived in a kind of limbo. Mathematicians used them when they had to, the way you might use a rickety bridge that happens to be the only way across a river. They worked. Nobody denied that. But nobody was quite comfortable saying they were real, and the name didn't help. Imaginary was coined by René Descartes in 1637, and he didn't mean it as a compliment. He was distinguishing between real roots of equations and imaginary ones, the ones that involved the square root of -1, and his language carried a clear implication. Real numbers are the proper ones, the ones that mean something. Imaginary numbers are pretenders. And the thing is, if you step back and think about it, the situation is actually quite funny, because the so-called real numbers include plenty of things that are deeply strange in their own right. Pi, for instance, an infinite, non-repeating decimal that you can never write down completely, or the square root of 2, which the ancient Pythagoreans found so disturbing that, according to legend, they drowned the man who discovered it. Or negative numbers themselves, which took centuries for European mathematicians to accept. The idea that you could have less than nothing was considered absurd for a very long time. And yet, eventually, all of these numbers got welcomed into the family. They got names, places on the number line, practical applications. They became respectable. The square root of -1 had to wait longer. And the thing that finally made it respectable, the thing that transformed it from a suspicious workaround into a full citizen of mathematics, was a picture. Imagine the standard number line. It stretches left and right, from -infinity on the left through 0 in the middle to positive infinity on the right. Every real number has a home on this line. Now imagine drawing a second line perpendicular to the first, crossing it at 0. This vertical line is the imaginary axis. The horizontal line is the real axis. And now, every point in the plane, the entire flat surface formed by these two axes, represents a number. A complex number. A number that has both a real part, measured along the horizontal, and an imaginary part, measured along the vertical. The number 3 plus 2i, for instance, is the point that sits 3 units to the right and 2 units up. The number -1 minus I is the point that sits 1 unit to the left and 1 unit down. This picture, which seems so simple once you see it, took more than 200 years to arrive. The Norwegian-Danish surveyor Caspar Wessel presented it in a paper in 1797. The Swiss-French mathematician Jean-Robert Argand published it independently in 1806. And the great Carl Friedrich Gauss, arguably the most prolific mathematician in history, developed it around the same time and used it extensively, though he was characteristically slow to publish. Today we call it the complex plane, or sometimes the Argand diagram. And the moment you draw that picture, the moment you see complex numbers as points in a plane, rather than as mysterious one-dimensional phantoms, everything changes. Because now, the arithmetic of complex numbers becomes geometry. Adding 2 complex numbers is the same as adding 2 arrows, 2 vectors, head to tail. And multiplying by a complex number does something even more beautiful. It rotates and stretches. If you take any point in the complex plane and multiply it by a complex number that sits on the unit circle, the circle of radius 1 centered at the origin, the effect is pure rotation. The point spins around the origin by the angle of that complex number. No stretching, no distortion, just a clean, smooth turn. Think about what that means. Multiplication, an arithmetic operation, the kind of thing you do with numbers on a page, turns out to be the same as rotation, a geometric operation, the kind of thing you do with objects in space. Numbers and shapes, algebra and geometry are secretly the same thing. And it gets deeper. Leonhard Euler, the great Swiss mathematician of the 18th century, found a formula that connects the exponential function, the trigonometric functions, and the imaginary unit in a single equation. The formula says that e raised to the power of I theta equals cosine theta plus I times sine theta. And when you set theta equal to pi, you get the most famous equation in all of mathematics. E to the I pi plus 1 equals 0. 5 fundamental constants of mathematics, E, I, pi, 1, and 0, linked in a single, short, astonishing relationship. Euler's formula is the bridge. It connects the exponential growth and decay that governs populations and radioactive decay and compound interest to the circular motion of sines and cosines to the imaginary unit that everyone had been so nervous about. And it tells you something deep. The imaginary number isn't an anomaly. It's a hinge. It's the thing that connects different areas of mathematics that seem to have nothing to do with each other. Without it, the connections are invisible. With it, they're obvious. And here's why this matters for quantum computing, though we won't get there for a while yet. In quantum computing, the state of a qubit, the fundamental unit of information, is described by 2 complex numbers. And the operations you perform on qubits, the quantum gates, are described by matrices of complex numbers. And the way those operations work is, geometrically, as rotations on a sphere, the Bloch sphere, which is a 3-dimensional generalization of the complex plane. The whole thing, from the ground up, is built on complex numbers and the geometry they make possible. And that geometry, the rotations and reflections and transformations, traces directly back to what Euler and Gauss and Argand were doing in the 1700s and 1800s. The math that was invented to make sense of an impossible number turned out to be the perfect language for describing how information can be processed at the quantum scale. But nobody knew any of that yet. In the early 1800s, complex numbers were finally respectable. They had a picture, a geometry, a place to live. Mathematicians were beginning to see them not as a necessary evil, but as a genuinely useful and beautiful extension of ordinary arithmetic. And the natural next question was, can we go further? Can we extend numbers into 3 dimensions, into 4, into higher dimensions? If the step from the real line to the complex plane was so fruitful, what would the next step look like? This question consumed one mathematician in particular for more than a decade. His name was William Rowan Hamilton. He lived in Dublin, and his obsession with extending complex numbers into 3 dimensions would lead him to one of the strangest and most consequential discoveries in the history of algebra. But it would also lead to something he didn't expect. Something that would make possible the entire framework of quantum mechanics and, ultimately, of quantum computing. He was about to discover that if you push numbers hard enough, they stop behaving like numbers. And when they do, the thing they start behaving like is something called a matrix. And there's a detail about Hamilton that I love, because it tells you something about the kind of person who pushes the boundaries of mathematics. Hamilton didn't come to his discovery easily. He spent over a decade, from roughly 1830 to 1843, trying to extend complex numbers into 3 dimensions. 13 years. Think about that. 13 years of dead ends, of rules that almost worked but didn't, of systems that satisfied some algebraic properties but violated others. He wrote letters to friends describing his frustration. He filled notebooks with attempts. His wife and children grew accustomed to seeing him stare into space at the dinner table, muttering about triplets. The problem was deep, and Hamilton didn't yet understand why it was deep. He was looking for a 3-dimensional number system that preserved all the nice properties of complex numbers. You could add, subtract, multiply, divide, and the result would always be another number in the same system. The technical term for such a system is a division algebra. And what Hamilton didn't know, what nobody would prove until later in the 19th century, is that division algebras over the real numbers exist only in dimensions 1, 2, 4, and 8. 1-dimensional is the real numbers, 2-dimensional is the complex numbers, 4-dimensional is Hamilton's quaternions, and 8-dimensional is the octonions, discovered independently around the same time by John Graves and Arthur Cayley. 3 dimensions simply don't work. The number system Hamilton was looking for doesn't exist, not because he wasn't clever enough to find it, but because the mathematics of the universe doesn't allow it. The moment on the bridge, when Hamilton realized he needed 4 dimensions and had to sacrifice commutativity, was the moment he stopped trying to extend numbers and started discovering something new. Quaternions aren't really numbers in the traditional sense. They're something richer, something more structured, something that encodes the geometry of 3-dimensional space in a way that ordinary numbers can't. And the sacrifice of commutativity. The acceptance that A times B doesn't equal B times A was the crucial step, the step that opened the door to a vast new landscape of algebraic structures, a landscape that would eventually include the matrix algebras used in quantum mechanics and quantum computing. And I want you to notice something about the pattern here. Complex numbers were forced into existence by the demands of polynomial equations. Quaternions were forced into existence by the demands of 3-dimensional geometry. In both cases, mathematicians didn't set out to invent new numbers for the fun of it. They were trying to solve problems, and the problems demanded tools that didn't exist yet. The tools were, in a sense, discovered rather than invented. They were already implicit in the structure of the problems. The mathematicians just had to see them. Meanwhile, in England, the story of matrices was unfolding along a parallel track. Arthur Cayley published his foundational paper on matrices in 1858. But the ideas had been in the air for some time. Cayley's work was connected to the study of determinants, which had been used since the 18th century to solve systems of linear equations. And systems of linear equations show up everywhere in science and engineering. If you have 3 variables and 3 equations, you can arrange the coefficients into a 3x3 grid, a matrix, and the rules for solving the system correspond to operations on that grid. What Cayley did was to take these grids of numbers and study them as mathematical objects in their own right, independent of any particular system of equations. He defined how to add them, multiply them, and find their inverses. He established their algebraic properties, and in doing so, he created a new branch of mathematics, linear algebra, the study of vectors, matrices, and linear transformations. Linear algebra is, today, probably the most practically useful branch of mathematics in existence. It's used in computer graphics, in machine learning, in statistics, in economics, in structural engineering, in signal processing, in control theory, in nearly every branch of science. The fact that you can watch a 3-dimensional animated movie is because of matrix transformations. The fact that your phone can recognize your face is because of linear algebra. The fact that Google can rank web pages is because of the eigenvalues of an enormous matrix. And the fact that a quantum computer works is because of linear algebra applied to complex vector spaces. But in 1858, none of this was foreseeable. Cayley was doing pure mathematics. He was studying structures. He was following his curiosity. And the structures he uncovered, the algebra of matrices and linear transformations, would wait decades for their applications to emerge. Some of those applications, like quantum mechanics and quantum computing, would take more than a century. There's a beautiful line that's often attributed to the mathematician G.H. Hardy, who wrote in his 1940 book, A Mathematician's Apology, that he had never done anything useful and that no discovery of mine has made or is likely to make, directly or indirectly, for good or ill, the least difference to the amenity of the world. Hardy was a number theorist, and he took pride in the supposed uselessness of his work. He believed that the value of mathematics lay in its beauty, not its utility. Hardy was wrong, as it happens. His work on number theory turned out to have applications in cryptography, in coding theory, and in other areas he couldn't have anticipated. But his attitude captures something important about the culture of pure mathematics in the 19th and early 20th centuries. Mathematicians studied what interested them, without regard for applications, and they were often proud of the irrelevance of their work. And yet, again and again, the irrelevant work turned out to be exactly what was needed when science reached a new frontier. Complex numbers for quantum mechanics, matrix algebra for the structure of atoms, group theory for particle physics, differential geometry for general relativity, topology for condensed matter physics. The pattern is so consistent, so reliable, that it starts to feel like more than coincidence. Hamilton was, by any measure, a prodigy. He had been appointed Royal Astronomer of Ireland and Professor of Astronomy at Trinity College Dublin at the age of 22, before he had even graduated. He was fluent in over a dozen languages, including Persian, Sanskrit, and Malay, which he had taught himself as a child. And his mathematical intuition was extraordinary. In the 1830s, he developed a reformulation of classical mechanics, now called Hamiltonian mechanics, that remains one of the pillars of theoretical physics to this day. The Hamiltonian, the function that describes the total energy of a system, is named after him, and it shows up everywhere in physics, including, as we'll see later, in quantum mechanics. The Schrödinger equation, the fundamental equation of quantum theory, is built around a Hamiltonian. So Hamilton's fingerprints are already all over this story, even before we get to his strangest contribution. But the thing that consumed Hamilton through the 1830s and into the 1840s was the search for three-dimensional complex numbers. He called them triplets. The idea seemed natural enough. A regular complex number has two components, a real part and an imaginary part. It lives in a two-dimensional plane. So surely, Hamilton reasoned, there should be a number with three components that lives in three-dimensional space. And if complex numbers could do rotation in 2 dimensions, then these triplets should be able to do rotations in 3 dimensions. He tried everything. For more than 10 years, he tried to make it work. He tried different rules of addition. He tried different rules of multiplication. He tried modifying the relationship between the components. Nothing worked. Every system he constructed either violated some basic rule of algebra, like the ability to divide, or produced contradictions. The three-dimensional extension of complex numbers simply would not come together. And then, on October 16, 1843, Hamilton was walking along the Royal Canal in Dublin with his wife, on their way to a meeting of the Royal Irish Academy, when the answer hit him. And the answer was this: forget 3 dimensions. You can't do it in 3 dimensions, but you can do it in 4. You need 4 components, not 3. one real part and three imaginary parts, which Hamilton labeled I, J, and K. And you need to give up one of the sacred rules of arithmetic. You need to accept that the order in which you multiply matters. A times B is not the same as B times A. Hamilton was so excited that he pulled out a knife and carved the fundamental equations into the stone of Brougham Bridge. I squared equals J squared equals K squared equals I times J times K equals -1. The bridge still stands, and there's a plaque there now marking the spot. Every year on October 16th, mathematicians make a pilgrimage to it. Hamilton called his four-dimensional numbers quaternions. And while quaternions themselves have had a complicated legacy, they're used today in computer graphics and spacecraft navigation, among other things. The lesson they taught was enormous. The lesson was this: when you extend the number system, you sometimes have to give up properties you thought were essential. In the case of quaternions, you give up commutativity, the rule that A times B equals B times A. And that's not a flaw, it's a feature. Because the physical world, it turns out, is full of operations where order matters. Rotating an object around one axis and then around another gives a different result depending on the order you do it in. Try it with a book. Hold it in front of you. Rotate it 90 degrees around a vertical axis, then 90 degrees around a horizontal axis. Now start over and do it the other way. Horizontal first, then vertical. The book ends up in a different orientation. Rotations in 3 dimensions do not commute, and this non-commutativity, this seemingly technical mathematical property that Hamilton stumbled onto while trying to solve a problem about numbers, would become, 80 years later, the central mystery of quantum mechanics. But that's a story for a later chapter. Meanwhile, in England, another mathematician was taking a different approach to the same kind of problem. Arthur Cayley, a London barrister who did mathematics on the side, as one did in Victorian England, began studying rectangular arrays of numbers in the 1850s. He was interested in what happens when you take a table of numbers, say a 2x2 grid, and define rules for adding, multiplying, and transforming them. He called these arrays matrices, from the Latin word for womb, because they generated determinants, which were another mathematical object people cared about at the time. And Cayley discovered something wonderful. Matrices obeyed most of the same rules as ordinary numbers. You could add them, you could multiply them, you could find inverses, the equivalent of division. There was even an identity element, a matrix that, when you multiplied it by any other matrix, left that matrix unchanged. The way multiplying a number by 1 leaves it unchanged. The identity matrix was the grid with 1s along the main diagonal and 0s everywhere else. But there was a catch, and it was the same catch Hamilton had encountered. Matrix multiplication is not commutative. If you multiply matrix A by matrix B, you get a different result than if you multiply B by A. The order matters. Again. Now, this might seem like an annoying limitation, and for many practical purposes it is. But Cayley, and later the mathematicians who built on his work, realized that the non-commutativity wasn't a bug. It was the key property that made matrices useful for describing transformations. When you multiply a matrix by a vector, a column of numbers representing a point in space, the matrix moves that point. It rotates it, stretches it, reflects it, projects it. Matrices are transformation machines. And the fact that the order of transformations matters, that rotating then reflecting is different from reflecting then rotating, is captured perfectly by the non-commutativity of matrix multiplication. Cayley also noticed something specific about 2x2 matrices with complex number entries. When you restricted yourself to a particular set of such matrices, the ones whose determinant equals 1 and whose inverse equals their conjugate transpose, a condition that would later be called unitarity, you got a group of transformations that preserved lengths and angles. They were rotations and reflections, symmetry operations, and the structure of that group turned out to be intimately connected to Hamilton's quaternions. The four-dimensional number system that Hamilton had carved into a bridge in Dublin could be represented perfectly and completely as a set of 2x2 complex matrices. So now we have three things that are secretly the same: quaternions, certain complex matrices, and rotations in three-dimensional space. Three different mathematical objects, invented for three different reasons by three different people in three different countries, all turning out to be descriptions of the same underlying structure. And none of them, not one, was invented with physics in mind. Hamilton was trying to extend the number system. Cayley was studying abstract algebra. Euler and Gauss were exploring the geometry of complex numbers. They were all doing pure mathematics, the kind that people call useless, the kind that gets defunded, the kind that students complain about. And within a single human lifetime, every one of these useless ideas would become indispensable. Because physics was about to break. And when it broke, the only language available to describe what replaced it was the language that these mathematicians had built. Let's go to Germany.
It's the late 1890s, and physics is feeling very confident about itself. Newtonian mechanics had been describing the motion of everything from cannonballs to planets for more than 2 centuries. James Clerk Maxwell had unified electricity and magnetism into a single, elegant framework and shown that light was an electromagnetic wave. Thermodynamics was well understood. The periodic table was filling in. There was a widespread feeling, an almost smug consensus, that physics was essentially done. The big questions had been answered. All that remained was polishing the details, pushing measurements to another decimal place. Lord Kelvin reportedly described 2 small clouds on the horizon of physics, 2 puzzles that hadn't been solved yet. He expected they would be cleared up soon enough. One of those clouds had to do with how light travels through space, and it would lead to Einstein's special relativity. But the other cloud, the one that matters for our story, had to do with something much simpler. It had to do with how hot things glow. You've seen this. A piece of metal in a blacksmith's forge starts out dark. Heat it up and it begins to glow a dull red. Hotter still and it turns orange, then yellow, then white hot. The color of the glow changes with temperature in a very regular, very specific way. Physicists had been measuring this carefully, and by the 1890s, they had beautiful, precise data showing exactly what spectrum of light a heated object emits at any given temperature. The data was clean, the curves were smooth, everything was well measured. The problem was that nobody could explain the data. Classical physics, the physics of Newton and Maxwell and Boltzmann, predicted something catastrophically wrong. When you applied the known laws of physics to calculate how a heated object should radiate energy across different wavelengths, the math said that the object should emit more and more energy at shorter and shorter wavelengths. Ultraviolet, then X-rays, then gamma rays, without limit. The total energy emitted should be infinite. An oven set to 400 degrees should, according to classical physics, blast you with lethal radiation the moment you open the door. This was called the ultraviolet catastrophe, and it wasn't a small discrepancy, the kind you could patch up with a minor correction. It was a total, spectacular failure of classical physics to describe one of the most basic phenomena in nature. The equations diverged to infinity. The theory predicted a world that would be lethal to life. And reality, obviously, was not like that.
5 years after Planck's reluctant quantum hypothesis, Albert Einstein took the idea and ran with it in a direction that Planck himself would never have gone. In 1905, Einstein published a paper on the photoelectric effect, the phenomenon in which light hitting a metal surface kicks electrons off the surface. The puzzle was this. Classical physics predicted that brighter light should produce faster electrons because brighter light carries more energy. But experiments showed something different. Brighter light produced more electrons, but they didn't move any faster. What made the electrons faster was using light of a higher frequency, bluer light. Red light, no matter how bright you made it, wouldn't kick electrons off at all if its frequency was below a certain threshold. Einstein's explanation was radical. Light, he said, doesn't just interact with matter in quanta, as Planck had suggested. Light itself is made of quanta,
discrete packets of energy that he called light quanta, and that we now call photons. Each photon carries an energy equal to Planck's constant times the frequency of the light. A single photon with enough energy can kick out a single electron. More photons means more electrons, but each individual photon-electron interaction is governed by the photon's frequency, not the overall brightness of the beam. This was, if you think about it, an extraordinary claim. Maxwell had shown, convincingly and beautifully, that light was a wave, electromagnetic radiation. It had wavelength, frequency, amplitude. It diffracted, it interfered, it polarized. Every wave-like behavior you could ask for, light exhibited. And now Einstein was saying that light was also made of particles. Not one or the other, but somehow both. A wave that was also a stream of particles. A continuous phenomenon that was also discrete. Einstein received the Nobel Prize in 1921 for this work, not for relativity, which was considered too speculative by the committee, but for the photoelectric effect. And the reason it mattered, beyond the specific phenomenon it explained, was that it extended Planck's quantum hypothesis from a statement about how matter emits and absorbs energy to a statement about the nature of light itself. Light was quantized, energy came in packets. The continuous, smooth, infinitely divisible world of classical physics was starting to crack, and through the cracks, a grainy, discrete, deeply strange new reality was becoming visible. Then came Niels Bohr. In 1913, Bohr proposed his model of the hydrogen atom, which applied quantum ideas to the structure of matter. In Bohr's model, an electron orbiting a hydrogen nucleus could only occupy certain specific orbits, corresponding to certain specific energy levels. The electron could jump from one orbit to another by absorbing or emitting a photon whose energy matched the difference between the two levels. Between the orbits, there was nothing. The electron couldn't exist at intermediate distances. It was as if the orbits were rungs on a ladder, and the electron could stand on one rung or another, but never between them. Bohr's model was a patchwork, a mixture of classical and quantum ideas that worked astonishingly well for hydrogen, but couldn't be extended to more complex atoms. It was a signpost, pointing in the right direction, saying, something like this is happening, without being a complete theory. The spectral lines of hydrogen, the specific wavelengths of light that hydrogen atoms emit, which had been measured with exquisite precision and which had defied explanation for decades, fell out of Bohr's model perfectly. The model predicted them exactly, down to the last decimal place. And those spectral lines, those precise wavelengths, were the data that Heisenberg would later organize into his mysterious tables. The numbers that he would multiply together using a rule he didn't recognize as matrix multiplication. The observable quantities from which he would build the first true quantum theory. And the scientific community took notice. Bohr's model, for all its limitations, had done something remarkable. It had taken the abstract quantum hypothesis, the idea that energy comes in discrete packets, and applied it to the structure of matter itself. The atom, which had been a mystery for millennia, was beginning to yield its secrets, and those secrets were quantized, discrete, grainy.
The electron could only occupy certain orbits. The energy of the atom could only take certain values. Between those values, there was nothing.
The quantum nature of energy, which Planck had introduced as a mathematical convenience and Einstein had extended to light, was now revealing itself as a fundamental feature of the architecture of matter. But the Bohr model, successful as it was for hydrogen, was clearly incomplete. When physicists tried to apply it to helium, the next simplest atom, with 2 electrons instead of 1, the model failed. The spectral lines didn't match, the orbits couldn't be made to work, and for larger atoms, the situation was even worse. The model was a brilliant sketch, a cartoon that captured something essential about the quantum nature of atoms, but it wasn't a theory. It didn't have the mathematical depth to handle complexity, and so, through the early 1920s, a generation of young physicists in Göttingen, Copenhagen, Munich, and Cambridge struggled to find the right mathematical framework. They tried extending Bohr's model. They tried adding more quantum rules. They tried quantizing classical mechanics in various ways. Arnold Sommerfeld in Munich added elliptical orbits and relativistic corrections, which improved the predictions for hydrogen but didn't solve the fundamental problems. Max Born in Göttingen worked on the mathematical foundations. Wolfgang Pauli, a fearsome young critic with an acid tongue and an unerring instinct for mathematical inconsistency, pointed out the flaws in every proposal, including his own. The atmosphere was one of creative desperation. Everyone knew the old physics was broken. Everyone could see the outline of the new physics in the experimental data, in the spectral lines, in the photoelectric effect, in the Compton scattering experiments that showed photons bouncing off electrons like billiard balls. But nobody could find the right mathematical language to describe it.
And then Heisenberg, the youngest and in some ways the boldest of the group, decided to stop looking for a picture and start looking for a calculus. He would abandon the attempt to visualize what was happening inside the atom. He would focus on what could be measured, and he would build a mathematical structure that connected measurements to each other. He wouldn't ask, "What is the electron doing?" He would ask, "What will I observe when I perform a measurement?" It was a philosophical shift as much as a mathematical one, and it worked. Because the mathematical structure he found, the algebra of tables of numbers that turned out to be matrices, was exactly the right language for quantum mechanics. A language that had been sitting on the shelf, developed by Cayley and others for abstract mathematical reasons, waiting for a physical problem that demanded it. So the sequence goes like this. Planck quantizes energy in 1900. Einstein quantizes light in 1905.
Bohr applies quantum ideas to the atom in 1913. And then, for about a decade, physicists struggle to extend these ideas to build a complete and consistent theory of the quantum world. They call this period the Old Quantum Theory, and it's marked by brilliant insights, ad hoc rules, and growing frustration. Everyone can see that the old classical framework is broken. Everyone can see that something quantum is going on. But nobody can figure out the right mathematical structure to describe it. And this is the moment when the mathematics that everyone had dismissed as having no practical value becomes essential. Because the right mathematical structure, when it finally emerges from Heisenberg's work on Helgoland, turns out to be matrix algebra, the very thing that Cayley had developed in the 1850s for purely abstract reasons. Waiting there, perfectly formed, ready to be applied to a problem that hadn't existed when it was created. In the autumn of 1900, a German physicist named Max Planck was staring at this problem in his office in Berlin. Planck was conservative, meticulous, deeply uncomfortable with revolutionary ideas. He had spent years trying to derive the correct formula for black-body radiation, the spectrum of light emitted by a perfect radiator using classical methods. And he had failed, just like everyone else. So Planck tried something desperate.
Instead of deriving the formula from first principles, he started with the experimental data, the beautiful, precise curves that the experimentalists had measured, and worked backwards. He asked, "What formula fits this data?" And he found one, a formula that matched the measurements perfectly. But when he tried to figure out what physical assumptions would produce that formula, he was forced into a corner.
The only way to make the math work was to assume that energy is not emitted or absorbed continuously, like a smooth flow of water from a tap, but in discrete packets, little chunks, indivisible minimum amounts. Planck called these chunks quanta, from the Latin word for how much. And the size of each quantum was determined by a new constant, a number that Planck calculated from the experimental data and that would eventually bear his name. Planck's constant, represented by the letter h, the energy of each quantum was equal to h, multiplied by the frequency of the radiation. High-frequency light came in big packets of energy. Low-frequency light came in small packets. And this simple assumption, energy comes in chunks, was enough to tame the ultraviolet catastrophe. At high frequencies, the energy packets were so large that the system couldn't afford to emit many of them, and so the emission dropped off, exactly as the experimental data showed. Planck wasn't happy about this. He considered the quantization of energy to be a mathematical trick, a convenient fiction, something he'd had to assume to get the right answer, but that surely didn't reflect how nature actually worked. He spent years trying to undo it, trying to find a classical explanation that would give the same formula, without requiring these awkward, indivisible energy packets. He never succeeded. And the reason he never succeeded is that the energy packets were real. Energy genuinely comes in quanta. The universe really is, at its most fundamental level, discrete rather than continuous, grainy rather than smooth. And this discovery, made reluctantly by a man who wanted nothing more than to preserve the classical worldview, is generally considered the birth of quantum physics. But here's what Planck didn't know, couldn't have known in 1900.
The mathematics that would be needed to describe this new quantum world, to make it precise, to turn it from a series of puzzling experimental results into a coherent theory, that mathematics already existed. It was sitting in textbooks and monographs and lecture notes, filed under pure mathematics, dismissed as abstract, labeled as having no practical application. Complex numbers, which had been developed to solve polynomial equations. Matrices, which had been developed to study systems of linear transformations. Vector spaces, which were an abstraction of the idea of arrows in space. Eigenvalues and eigenvectors, which described how transformations stretch and rotate things. All of it was there, ready and waiting, like a toolkit that had been assembled over centuries by craftsmen who had no idea what it would eventually be used to build. Physics had broken.
And the tools to fix it were the ones that mathematicians had forged, for their own reasons, in their own time, following their own curiosity. The abstract, impractical, supposedly pointless mathematics was about to become the most useful mathematics in the world. And the person who would make that connection, the one who would reach into the mathematical toolkit and pull out exactly the right instrument, was a 23-year-old with hay fever, sitting alone on a rocky island in the North Sea, trying to escape the pollen season. His name was Werner Heisenberg, and in June of 1925, he was miserable. His face was swollen, his eyes were streaming. The pollen count in Göttingen, where he was working as an assistant to the physicist Max Born, was unbearable. So Heisenberg did what any sensible young German physicist with severe allergies would do. He got on a train, then a boat, and went to Helgoland, a tiny, windswept, practically treeless island about 50 miles off the German coast in the North Sea.
There was almost no vegetation there. No grass, no trees, no flowers. Just red sandstone cliffs, seabirds, wind, and salt air. It was perfect for someone who couldn't stop sneezing. And it was there, over the course of a few extraordinary days and nights, largely alone and largely sleepless, that Heisenberg would write down the equations that mark the true beginning of quantum mechanics. The beginning of a theory that would explain the behavior of atoms, of molecules, of light, of all matter at its most fundamental level. And the remarkable thing, the thing that connects this chapter to everything we've been talking about, is the mathematics he used. Because Heisenberg, without quite knowing what he was doing, reinvented matrix multiplication.
To understand what Heisenberg was trying to do, you need to understand the problem he was working on. Since Planck's discovery in 1900 and Einstein's extension of it to light in 1905, when Einstein proposed that light itself came in quanta called photons, physicists had been struggling to build a coherent picture of the atom. The Danish physicist Niels Bohr had proposed a model in 1913 in which electrons orbited the nucleus of an atom in specific quantized orbits, like planets orbiting a sun, but restricted to certain allowed distances. This model worked surprisingly well for hydrogen, the simplest atom, with one electron orbiting one proton. It correctly predicted the wavelengths of light that hydrogen emits and absorbs, the bright colored lines that show up when you pass hydrogen light through a prism. But for anything more complicated than hydrogen, Bohr's model started to fail. And worse, it was conceptually uncomfortable. Why should electrons be restricted to certain orbits? What happened between the orbits? If an electron could only exist in orbit number 1 or orbit number 2, but never in between, what did it do when it jumped from one to the other? Did it teleport? Did it pass through the forbidden zone instantaneously? Nobody knew. Heisenberg's approach was radical, and it was born of frustration. He decided to stop trying to picture what was happening inside the atom, stop trying to visualize electron orbits, stop trying to describe trajectories. Instead, he would focus only on things that could actually be observed, the frequencies and intensities of the light that atoms emit, the spectral lines, the numbers you could measure in a laboratory. And he would try to build a mathematical structure that connected those observable quantities to each other, without worrying about what the unobservable reality inside the atom looked like. So there he was on Helgoland, working through the night, scribbling equations on sheets of paper. And the mathematical objects he was working with were tables of numbers. Each table had rows and columns, and the entries represented the probability of a transition from one atomic energy level to another, multiplied by the frequency of the emitted light. Heisenberg needed to combine these tables to find the rule for how two such tables should be multiplied together. And here's the moment. Heisenberg worked out the multiplication rule by a kind of physical reasoning, asking what combinations of transitions were possible and how their probabilities should be combined. When he wrote it down, the rule looked unfamiliar. It was complicated. It was not the simple term-by-term multiplication you'd expect from ordinary arithmetic. To get the entry in a particular row and column of the product, you had to take pairs of numbers from the two tables, multiply them, and sum them all up.
Each entry in the result was a sum over products. Heisenberg didn't realize it, but he had rediscovered the rule from multiplying matrices. The same rule that Arthur Cayley had formalized 70 years earlier in England. The same algebra that had been sitting in pure mathematics textbooks, studied for its abstract beauty, taught to small numbers of graduate students, generally regarded as elegant but useless. Heisenberg had arrived at it from the completely different direction of trying to describe atomic physics, and he had no idea that the tool already had a name. He sent his work to Max Born in Göttingen, and Born, who was older and had a broader mathematical education, recognized what he was looking at almost immediately. He later recalled that when he read Heisenberg's paper and saw the multiplication rule, he was up all night, unable to sleep, because the rule was so familiar. It took him a few days, but he placed it. These were matrices.
Heisenberg had been doing matrix algebra all along, and suddenly everything clicked. The entire mathematical framework of linear algebra, the theory of matrices and vectors and eigenvalues and transformations that had been developed over the previous century, could be applied to quantum physics. Born, together with his student Pascual Jordan, spent the summer of 1925 rapidly developing this idea into a complete, coherent mathematical framework. They published a paper in September, followed by a more comprehensive one in November, the famous Drei-Männer-Arbeit, the three-man paper, by Born, Heisenberg, and Jordan. In this paper, the laws of quantum mechanics were stated for the first time in the language of matrices. And here's the punchline. The thing that connects all the threads we've been following. The most distinctive feature of the new quantum mechanics, the thing that made it most different from classical physics, was this. The matrices that represented observable physical quantities did not commute. If you had a matrix P representing the momentum of an electron and a matrix Q representing its position, then P times Q was not equal to Q times P. The difference between PQ and QP was not zero. It was equal to I times h bar, where I is the square root of -1 and h bar is Planck's constant divided by 2 pi. Think about that. The most fundamental fact about quantum mechanics, the fact that distinguishes it from all of classical physics, the fact from which the uncertainty principle flows, the fact that explains why you cannot simultaneously know the exact position and the exact momentum of a particle. That fact is expressed as a statement about non-commuting matrices involving the imaginary number.
Two mathematical objects that were invented for seemingly abstract reasons, matrices and complex numbers. One from a study of algebraic transformations, and the other from a struggle with polynomial equations, turned out to be not merely useful for describing quantum mechanics. They turned out to be essential. The theory could not be stated without them. The universe, at its deepest level, speaks in the language of complex matrices, and nobody designed it that way. Nobody sat down and said, let's find a physics that uses these mathematical tools. Heisenberg didn't even know what matrices were. He discovered the physics, and the physics dragged the mathematics in with it. Hamilton's non-commuting quaternions, which he had discovered in a flash of insight on a bridge in Dublin in 1843, had been waiting 82 years for a physical system that actually exhibited non-commutativity. And now, here it was.
Position and momentum, the most basic quantities in physics, did not commute. The math had predicted a feature of reality before anyone knew that reality had that feature. And this raises, once again, the question we started with tonight. Is mathematics something we invent or something we discover? But Heisenberg's matrix mechanics, beautiful as it was, had a problem. It was mathematically demanding and physically opaque. Calculating with infinite dimensional matrices was technically challenging, and the formalism didn't give you any intuitive picture of what was happening inside an atom. It was like having a recipe that produced perfect meals, but was written in a language you couldn't read aloud. Which is why, less than a year later, another approach to quantum mechanics burst onto the scene. One that seemed much more intuitive, much more visual, and much easier to work with. It was proposed by an Austrian physicist named Erwin Schrödinger, and it centered on a wave equation that looked reassuringly like the kinds of equations physicists had been solving for centuries. Instead of abstract matrices, Schrödinger offered a smooth, continuous wave function that evolved over time according to a differential equation. You could picture it. You could draw it. You could see the electron as a kind of vibrating cloud around the nucleus. Physicists loved it. Schrödinger's inspiration came from an unlikely source. In November 1924, Einstein had received a paper from an unknown Indian physicist named Satyendra Nath Bose, who had derived Planck's radiation law using a new statistical method. Einstein was impressed, translated the paper into German, and helped get it published. But Einstein also had a further thought.
He applied Bose's method not to photons but to atoms, and in doing so, he encountered a recent doctoral thesis by a French physicist named Louis de Broglie. De Broglie had proposed something audacious. If light, which everyone thought was a wave, could behave like a particle, as Einstein had shown with the photoelectric effect, then perhaps matter, which everyone thought was made of particles, could behave like a wave. De Broglie even wrote down a formula for the wavelength of a matter wave. It was Planck's constant divided by the momentum of the particle. The more massive or the faster the particle, the shorter its wavelength. For everyday objects, the wavelength is inconceivably tiny, far too small to detect. But for electrons, which are very light, the wavelength is comparable to the spacing between atoms in a crystal.
And indeed, in 1927, Clinton Davison and Lester Germer in New York, and independently George Paget Thompson in Aberdeen, showed that electrons could be diffracted by crystals, just as X-rays could. Electrons behaved as waves. De Broglie was right. Einstein mentioned de Broglie's idea in a footnote to one of his papers, and that footnote caught Schrödinger's attention. If particles can behave like waves, Schrödinger reasoned, then there should be a wave equation that governs their behavior. Just as Maxwell's equations govern electromagnetic waves and the classical wave equation governs vibrations on a string. Over the winter holidays at the end of 1925, Schrödinger retreated to a villa in the Swiss Alps, reportedly in the company of a woman who was not his wife. The identity of this companion remains one of the more intriguing mysteries of physics history. And over the course of a few weeks, he derived his equation.
The equation describes how the wave function, the complex-valued function psi, evolves over time. On one side of the equation is the time derivative of psi, multiplied by I times h bar, I being the imaginary unit and h bar being Planck's constant divided by 2 pi. On the other side is the Hamiltonian operator applied to psi. The Hamiltonian, remember, is the mathematical object that Hamilton invented in the 1830s to describe the total energy of a classical system. In quantum mechanics, the Hamiltonian becomes an operator, a mathematical machine that acts on the wave function and produces a new wave function. It incorporates both the kinetic energy, which is related to the curvature of the wave function in space, and the potential energy, which depends on the forces acting on the particle. The equation is beautiful, compact, and extraordinarily powerful. From it, you can derive the energy levels of the hydrogen atom, reproducing Bohr's results exactly. You can calculate the shapes of electron orbitals, the probability clouds that determine the chemical properties of atoms. You can predict the tunneling of particles through barriers, the phenomenon that makes nuclear fusion in the sun possible. You can describe the behavior of superconductors, superfluids, lasers, and semiconductors. Essentially, every quantum phenomenon that has ever been observed can be described by solutions to Schrödinger's equation. And right there, in the equation, impossible to remove, is the imaginary unit I. It sits on the left side, multiplying the time derivative. If you try to remove it, if you try to write a version of the equation using only real numbers, the equation stops describing the correct physics. Real-valued wave equations, like the classical wave equation for a vibrating string, produce solutions that oscillate but don't propagate. They describe standing waves, not traveling waves.
To get a wave that moves, that carries quantum information from one place to another, you need the complex phase. You need the I. This is deeply strange when you stop to think about it. The most fundamental equation in quantum physics, the equation that describes the behavior of every piece of matter in the universe, contains the square root of -1 as a structural element. Remove it, and the equation doesn't work. The imaginary number is a load-bearing pillar of reality. Schrödinger's equation, published in early 1926, is perhaps the most important equation in all of quantum mechanics. And for our story, the story of mathematics that was considered meaningless, it has a crucial feature. The wave function, the solution to Schrödinger's equation, is not a real valued function. It is a complex valued function. It takes complex numbers as its values.
The quantity psi, the wave function, which describes the state of a quantum system, is a function whose output, at every point in space and at every moment in time, is a complex number. A number with a real part and an imaginary part. A number that lives in the complex plane of Argand and Gauss and Euler. And this is not a mathematical convenience. It's not a trick like Planck's quanta initially seemed to be. Complex numbers are genuinely, fundamentally, irreducibly necessary for quantum mechanics. You cannot write Schrödinger's equation with real numbers only. The equation has an I in it, the square root of -1, sitting right there in the middle, and if you try to remove it, the equation falls apart. The time evolution of quantum systems requires complex numbers the way arithmetic requires 0. Now, Schrödinger's wave function was beautiful, but it raised an immediate question. What does it mean?
If the wave function is a complex valued function and complex numbers are not directly observable, you can never measure a complex number with a physical instrument. Then what is the wave function a wave of? What's waving? The answer came from Max Born, the same Max Born who had recognized Heisenberg's matrices. Born proposed in 1926 what we now call the Born rule. The rule says this: the wave function itself is not directly observable. But if you take its magnitude squared, if you take the complex number at each point, multiply it by its complex conjugate, and get a real number, that real number gives you the probability of finding the particle at that point. And notice what's happening here. Remember when we talked about complex numbers and the complex conjugate? When you multiply a complex number by its conjugate, you flip the sign of the imaginary part and multiply. The result is always a real number, always positive, always measurable.
The impossible number, the square root of -1, lives at the heart of the wave function. But what you actually observe, the probability, is real. The imaginary part is there, doing essential work, shaping the interference patterns, determining the phases, governing how waves add and cancel, but it never shows its face directly. The universe uses complex numbers in its internal calculations, but presents only real numbers to the observer. Let me dwell on this a little longer, because it's really the heart of the whole story. The question of whether complex numbers are merely convenient or genuinely necessary for quantum mechanics was debated for years after Schrödinger's equation was published. Some physicists hoped that you could reformulate quantum mechanics using only real numbers, treating the imaginary unit as a bookkeeping device, a shorthand for keeping track of two real-valued equations at once. And at a superficial level, this seems possible. Any complex number, a plus ib, can be written as a pair of real numbers, a and b. Any equation involving complex numbers can, in principle, be rewritten as a pair of coupled equations involving real numbers only. But in 2022, a team of physicists published a result that settled the question definitively, at least for the standard formulation of quantum mechanics. They showed that a real number version of quantum mechanics makes different predictions from the standard complex number version, and that those predictions can be tested experimentally. When the experiments were done, the complex number version won. The universe genuinely uses complex numbers in its quantum mechanical descriptions. They are not a convenience. They are a necessity. And the reason, if you trace it down, has to do with the phase of a complex number.
Remember the complex plane? The picture where every complex number is a point with a distance from the origin and an angle measured from the positive real axis. The distance is the magnitude. The angle is the phase. In quantum mechanics, the magnitude of a complex amplitude gives you the probability of a measurement outcome via the Born rule. But the phase gives you something else entirely. The phase governs interference. When two quantum states combine, their complex amplitudes add together, not their probabilities. And when two complex numbers with different phases are added, they can reinforce each other if their phases are similar, or cancel each other out if their phases are opposite. Constructive and destructive interference. The same phenomenon that makes ocean waves build up or cancel. The same phenomenon that makes sound waves create beats. The same phenomenon that makes light waves create the colored fringes in a soap bubble.
Interference is ubiquitous in physics, and it's what gives quantum mechanics its distinctive character. A quantum computer works by exploiting interference. The algorithms are designed so that the paths leading to the wrong answer interfere destructively. Their complex amplitudes cancel, and the paths leading to the right answer interfere constructively. Their complex amplitudes reinforce. When you measure at the end, the right answer has a large probability, and the wrong answers have small or zero probabilities. And this interference requires complex phases. Real numbers don't have phases, they're just positive or negative. They can cancel, yes, +1 plus -1 equals 0. But they can't do the subtle angle-dependent interference that complex numbers can. They can't encode the rich structure of quantum states. The phases of complex amplitudes carry information about the relationships between different quantum states, information that is essential for the functioning of quantum algorithms. So when we say that the square root of -1 is at the heart of quantum computing, we mean something very specific. We mean that the ability of complex numbers to carry phase information and the ability of those phases to produce interference is the mechanism by which quantum algorithms achieve their power. Without complex numbers, there is no interference. Without interference, there is no quantum speedup. Without quantum speedup, there is no reason to build a quantum computer. The number that Cardano called useless is the reason quantum computers are useful. This is worth sitting with for a moment. The most fundamental description we have of physical reality, the wave function, is complex valued. The universe keeps its books in complex arithmetic. And the only reason we have access to the results is the Born rule, which is, mathematically, the process of multiplying by the complex conjugate. The same operation that Bombelli worked out in 1572 for his impossible numbers. The same operation that appears in the definition of the magnitude of a complex number. The same operation that makes a complex number real. 4 centuries of mathematical development, from Cardano's reluctant square roots, to Euler's formula, to the complex plane, to the theory of complex valued functions, all of it flowed into this moment. The universe, when physics finally peeled back enough layers to see its fundamental structure, turned out to be speaking a language that mathematicians had been developing, slowly, painstakingly, for entirely unrelated reasons, for hundreds of years. And now Schrödinger had a wave equation, and Heisenberg had matrix mechanics, and they seemed to be saying different things. Schrödinger described quantum systems in terms of smooth, continuous wave functions evolving over time. Heisenberg described them in terms of discrete matrices that obeyed algebraic rules. The two approaches looked nothing alike. Physicists began choosing sides. The wave people and the matrix people argued about which formulation was the true one. But within months, Schrödinger himself proved that the two formulations were mathematically equivalent. They were the same theory, expressed in different languages. Matrix mechanics and wave mechanics were like two maps of the same terrain, one drawn in the language of algebra and the other in the language of differential equations. The features they described were identical. And it was a young British physicist named Paul Dirac who saw the deepest version of this equivalence and who built the framework that unified both approaches into something more abstract, more powerful, and more beautiful than either one alone.
Dirac was, by all accounts, an unusual person. Quiet, precise, almost unnervingly literal. When a colleague at a lecture once said, "I don't understand the equation on the top right of the blackboard," Dirac reportedly replied, "That is a statement, not a question." He thought in mathematics the way most people think in words, and his sense of mathematical beauty was so refined that he once said he would rather have equations be beautiful than have them be correct, because beauty was a more reliable guide to truth. Dirac's insight was that both Heisenberg's matrices and Schrödinger's wave functions were representations of something deeper. He introduced a notation, now called Dirac notation or Bra-Ket notation, that abstracted away the specific representation and focused on the underlying mathematical structure. In Dirac's framework, the state of a quantum system is described by a ket, written as a vertical bar, followed by a label and a closing angle bracket. The state of an electron in, say, the ground state of hydrogen would be written as ket psi. The ket is not a matrix, and it's not a wave function. It's an abstract vector in a complex vector space, a mathematical object that lives in what's called a Hilbert space, an infinite-dimensional generalization of the complex plane. And here's the connection to everything we've been building. A Hilbert space is a vector space over the complex numbers, equipped with an inner product that allows you to measure lengths and angles. It's the abstract version of the same geometry that Argand and Gauss saw when they drew complex numbers as points in a plane. The axes of the Hilbert space are the possible states of the quantum system, and the quantum state is a vector in that space, a kind of arrow pointing in a particular direction. The coefficients of that vector, the numbers that describe how much of the arrow points along each axis, are complex numbers. In Dirac's notation, measuring a quantum system corresponds to projecting the state vector onto one of the axes. The probability of a particular measurement outcome is the square of the length of that projection. And this is, once again, the Born rule. Take the complex coefficient, multiply by its conjugate, get a real number. So quantum mechanics, in its most abstract and general form, is geometry in a complex vector space. It's the study of how vectors rotate and project and interfere in a space whose coordinates are complex numbers. And the operations that rotate those vectors, the physical processes that change one quantum state into another, are represented by matrices. Specifically, by unitary matrices, the ones whose conjugate transpose is their inverse, the ones that preserve the length of vectors, the ones that Cayley had studied in the 1850s. The entire mathematical apparatus that we followed, from Cardano to Bombelli, to Euler, to Gauss, to Hamilton, to Cayley, the complex numbers and the matrices and the vector spaces and the eigenvalues, all of it comes together in quantum mechanics. Every piece was needed, every piece was used, and every piece had been developed originally for reasons that had nothing to do with physics. Dirac published his formulation in the late 1920s, and it became the standard language of quantum physics. His notation is used in every quantum mechanics textbook in the world. And when, decades later, physicists and computer scientists began thinking about how to use quantum mechanics to process information, to build a new kind of computer, they would reach for Dirac's framework. The qubits, the gates, the measurements, the entanglement, all of it would be described in Bra-Ket notation, using complex vectors and unitary matrices in Hilbert spaces.
But that development was still 60 years away. And to understand why it took so long, and what made quantum computing so different when it finally arrived, we need to take a detour. Because the idea of a quantum computer only makes sense if you first understand what a regular computer is. And the strange thing is, the regular computer, the one in your pocket, the one on your desk, the one that runs the modern world, was also born from pure mathematics, from a question that nobody expected to have practical consequences. So let's step away from the quantum world for a while. We'll come back to it. Right now, I want to tell you about a quiet, socially awkward, profoundly brilliant young man in Cambridge, England, who liked long-distance running and who, in 1936, was thinking about a problem that had been posed by one of the greatest mathematicians of the 20th century, David Hilbert.
And who, in the process of solving that problem, accidentally invented the theoretical foundations of every computer on Earth. The problem was called the Entscheidungsproblem, which is German for the decision problem, and Hilbert had posed it as part of a grand program to put all of mathematics on a solid, unshakable foundation. The question, stripped to its essence, was this: is there a mechanical procedure, a step-by-step algorithm, that can determine whether any given mathematical statement is true or false? Can you build a machine, at least in principle, that takes in any mathematical proposition and after some finite amount of work spits out either true or false? Hilbert believed the answer was yes. He thought mathematics was complete and consistent, that every true statement could be proved, and that a systematic method for finding those proofs must exist. But in 1931, the Austrian logician Kurt Gödel had delivered a devastating blow to Hilbert's program. Gödel proved that any sufficiently powerful mathematical system, one powerful enough to describe basic arithmetic, must contain statements that are true but unprovable within the system. Mathematics could never be both complete and consistent. There would always be truths beyond the reach of proof. And then, in 1936, Alan Turing went further. To answer Hilbert's question, Turing first had to define precisely what a mechanical procedure meant. What is computation? What does it mean to follow an algorithm? And Turing's answer to this definitional question turned out to be more consequential than his answer to Hilbert's. Turing imagined a hypothetical device, an infinitely long tape divided into cells, each cell containing a symbol, say a 0 or a 1. A read-write head that could move along the tape, one cell at a time, reading the current symbol, writing a new one, and moving left or right. And a set of instructions, a finite table of rules, that told the head what to do at each step based on the current symbol and the machine's current internal state. That's it. That's the whole device. A tape, a head, and a rule table. Turing called it an automatic machine. We call it a Turing machine. And Turing proved something remarkable about it. He proved that this absurdly simple device, with its tape and its head and its little table of rules, could compute anything that any mechanical procedure could compute. Any algorithm, any calculation, any procedure that you could describe precisely enough to follow step by step, could be carried out by a Turing machine. The specific machine might be different for each problem, but the class of Turing machines, taken together, was universal. It captured the full extent of what computation could mean. And then Turing proved his main result. He showed that there exist problems that no Turing machine can solve. Specifically, there is no general procedure for deciding whether an arbitrary Turing machine, given an arbitrary input, will eventually halt or will run forever. The halting problem is undecidable. And from this, it follows that Hilbert's Entscheidungsproblem has no solution. There is no universal algorithm for determining mathematical truth. But here's what matters for our story. Turing had defined computation. He had given it a precise mathematical meaning, and in doing so, he had, without realizing it, laid the theoretical foundation for every computer that would ever be built. Because every modern computer, from the laptop on your desk to the phone in your pocket to the supercomputers running climate simulations, is, at its core, a physical realization of Turing's abstract machine. The tape became memory. The read-write head became the processor. The rule table became software.
The details changed enormously. transistors instead of hypothetical tape, silicon chips instead of imaginary heads. But the fundamental logic, the mathematical skeleton, is the same. And that logic, the logic of classical computing, runs on a very specific kind of mathematics: binary arithmetic, Boolean logic, the algebra of true and false, 0 and 1, on and off. A classical computer takes binary inputs, applies logical operations, and produces binary outputs. And the logical operations, the AND gates and OR gates and NOT gates that make up the circuitry of a processor, are simple, deterministic, and commutative. The order in which you apply them might matter for practical purposes, but the underlying algebra is tidy and well-behaved. Classical bits are honest objects. Each one is either 0 or 1, never anything in between, never uncertain, never ambiguous.
Now, in 1947, three physicists at Bell Labs in New Jersey, William Shockley, John Bardeen, and Walter Brattain, built the first transistor. A transistor is essentially a tiny switch that can be turned on or off by an electrical signal, and it's the physical device that makes binary computing practical. Before transistors, computers were made of vacuum tubes, which were bulky, hot, unreliable, and expensive. Transistors were small, cool, reliable, and cheap. And as manufacturing improved, they got smaller and smaller. By the 1960s, engineers were fitting thousands of transistors onto a single chip of silicon. By the 1980s, millions. By today, billions. The processor in your phone contains something like 15 billion transistors, each one a tiny switch that is either on or off, representing a 0 or a 1. And that connection between Turing's abstract machine and the physical device in your pocket took decades and thousands of people to build. Turing's paper was published in 1936. The first electronic general-purpose computer, ENIAC, was completed in 1946. It weighed 30 tons, filled a room, used 17,000 vacuum tubes, and consumed enough electricity to dim the lights in an entire section of Philadelphia when it was switched on. It could perform about 5,000 additions per second. Your phone, by comparison, can perform roughly 15 billion operations per second. The gap between ENIAC and your phone is a factor of about 3 million, and it was closed over the course of 70 years, driven almost entirely by improvements in the physical hardware that implemented Turing's abstract idea. And the key improvement, the one that made everything else possible, was the transistor. Before the transistor, computers used vacuum tubes as switches. A vacuum tube is essentially a small glass bulb, roughly the size of your thumb, containing metal electrodes in a vacuum. An electrical signal at one electrode controls the flow of current through the tube, turning it on or off. Vacuum tubes work, and they enabled the first generation of electronic computers. But they're bulky, fragile, hot, and power-hungry. ENIAC's 17,000 vacuum tubes burned out at a rate of several per day, and the engineers spent much of their time identifying and replacing dead tubes. Shockley, Bardeen, and Brattain's transistor, demonstrated in December 1947, was made of a piece of germanium, a semiconductor, with wires attached. It was small, solid, cool, and reliable. It did the same job as a vacuum tube, acting as a switch that could be turned on or off by an electrical signal. But it could be made much smaller, much cheaper, and much more durable. And crucially, it could be miniaturized. By the late 1950s, engineers at Fairchild Semiconductor and Texas Instruments had figured out how to fabricate multiple transistors on a single piece of silicon, creating the integrated circuit. By the late 1960s, you could fit hundreds of transistors on a chip. The Intel 4004, released in 1971, packed 2,300 transistors into a single microprocessor. The Intel Pentium, in 1993,
had 3.1 million. A modern Apple M series chip contains over 100 billion. Each transistor is a switch, on or off, 0 or 1. And the logic of computation, the AND gates and OR gates and NOT gates that implement Turing's abstract machine, is built by connecting these switches in specific patterns. The mathematics of classical computing, Boolean algebra, is the mathematics of these switch configurations. It's clean, deterministic, and, to a mathematician, somewhat boring.
The switches are either open or closed. The bits are either 0 or 1. There's no ambiguity, no uncertainty, no phase, no interference. And this is where the contrast with quantum computing becomes vivid. In a classical computer, the state of a register of n bits is a string of n zeros and ones. There are 2 to the n possible strings, but the register is always in exactly one of those states. It represents one number at a time, and computation proceeds by manipulating that number step by step. In a quantum computer, the state of a register of n qubits is a vector in a 2 to the n dimensional complex vector space. The register is not in one of the 2 to the n basis states. It is in a superposition of all of them simultaneously, complex coefficients that encode both probabilities and phases. And a quantum gate operates on this entire superposition at once, transforming all 2 to the n amplitudes in a single step. This is the sense in which a quantum computer is parallel.
It processes exponentially many states simultaneously, not by having exponentially many processors, but by living in an exponentially large mathematical space. The parallelism is not physical, it's mathematical. It's the parallelism of a vector being rotated in a high-dimensional space, where a single rotation moves all of the vector's components at once. And the mathematical space in which this happens, the complex Hilbert space of the qubit register, is built from exactly the tools we've been tracing throughout this story. Complex numbers, because the amplitudes have phases. Vectors, because the state is a direction in a space. Matrices, because the operations are linear transformations. Tensor products, because the space of n qubits is the tensor product of an individual qubit spaces. This is why the title of Yanofsky and Minucci's textbook is Quantum Computing for Computer Scientists. Because the leap from classical to quantum computing is, at its heart, a leap from Boolean algebra to complex linear algebra. From the mathematics of switches to the mathematics of waves. From on and off to alpha times ket 0 plus beta times ket 1. And the second kind of mathematics, the complex kind, the one with the imaginary numbers and the phases and the rotations, was there waiting, fully developed, when computer scientists finally came looking for it. And this exponential shrinking, famously described by Moore's law, the observation that the number of transistors on a chip roughly doubles every 2 years, has driven the entire digital revolution. Every advance in computing power, from the first room-sized mainframes to the smartphones in our pockets, has come from making transistors smaller, packing more of them onto a chip, and switching them faster. But there's a limit. And by the early 21st century, that limit was becoming uncomfortably visible. The smallest transistors in production today are about 50 atoms across. When you get that small, you start running into quantum effects. Electrons, which are supposed to stay obediently on one side of a barrier, start tunneling through to the other side. A purely quantum mechanical phenomenon where a particle has a non-zero probability of passing through a wall that classical physics says it shouldn't be able to cross. Bits that are supposed to be cleanly 0 or 1 start getting fuzzy. The sharp, deterministic, well-behaved logic of classical computing starts to break down. The quantum world, which physicists had been studying for decades, was leaking into the engineering.
And this is where the story turns. Because in the early 1980s, a few physicists began asking a question that sounds, at first, like the kind of thing you'd say after too much coffee at a late-night seminar.
What if, instead of fighting quantum effects, instead of trying to keep them out of your computer, you used them? What if you built a computer that worked with quantum mechanics rather than against it? What if the weirdness, the superposition, the entanglement, the non-commutativity, all the things that made quantum physics so strange and so unintuitive, what if those were features rather than bugs? The first person to articulate this idea clearly, to stand up in front of an audience of physicists and say it out loud, was Richard Feynman. It was 1981. Feynman was at a conference on physics and computation at MIT, and he was thinking about a simple but profound question. Can you simulate a quantum system on a classical computer? That is, if you have a molecule or an atom or a collection of particles obeying the laws of quantum mechanics, can you predict its behavior using an ordinary computer? And the answer, Feynman realized, was sort of, but not really. You can simulate small quantum systems on a classical computer. A few particles, a simple molecule. But as the system gets bigger, the amount of computation required explodes exponentially. Add one more particle and the computation roughly doubles. Add 10 more and it's 1,000 times harder. Add 50 and it's beyond the capacity of any computer that could ever be built using classical methods. The fundamental reason is that a quantum system of n particles lives in a Hilbert space whose dimension grows exponentially with n. To describe the state of 50 entangled particles, you would need 2 to the power of 50 complex numbers, which is about 1,000,000 billion numbers. For 300 particles, you'd need more numbers than there are atoms in the observable universe. Classical computers can't handle this. They drown in the exponential growth. And the reason they drown is that they're trying to describe a fundamentally quantum system using the language of classical bits.
Zeros and ones. Clean, deterministic, commutative. The language is too narrow. It's like trying to describe a sphere using only straight lines. You can approximate it, but the approximation gets harder and harder the more detail you need. Feynman's insight was sharp and direct. He said, essentially, nature computes quantum mechanically. If you want to simulate nature, you should use a computer that also computes quantum mechanically. A quantum computer. He didn't specify what such a computer would look like. He didn't give blueprints. He just pointed out the logic, the exponential explosion that makes quantum simulation intractable on a classical computer would be natural and effortless on a computer that itself operated according to quantum rules. Because a quantum computer, whatever it turned out to be, would natively inhabit the same exponentially large Hilbert space that the quantum system lived in. It would speak the language of the system it was simulating.
And that language, as we've spent the last several chapters seeing, was the language of complex numbers, matrices, and vector spaces. The supposedly impractical mathematics, the language that Cardano had stumbled onto, that Euler had connected to rotations, that Heisenberg had unknowingly reinvented, that Schrödinger had embedded in his wave equation, that Dirac had abstracted into bracket notation. Feynman was proposing, in effect, to build a physical machine that computed directly in that language, not translating quantum problems into classical binary, but processing them in their native mathematical form. But Feynman's idea was a vision, not a theory. It would take another physicist to turn the vision into a precise theoretical framework. And that physicist was David Deutsch. Deutsch was, and is, a theoretical physicist at the University of Oxford, a deep thinker with an unusual combination of mathematical rigor and philosophical ambition.
In 1985, he published a paper that defined for the first time what a quantum computer actually is in mathematical terms.
Deutsch described the quantum analog of a Turing machine. Where a classical Turing machine manipulates bits, each one definitively 0 or 1, Deutsch's machine manipulates qubits, quantum bits, each one a quantum system that can be in a superposition of 0 and 1. And here's where all the mathematics we've been building toward comes together. Because a qubit, in Deutsch's framework, is not described by a single value, 0 or 1. A qubit is described by a vector in a two-dimensional complex vector space. Let's unpack that, because it's important. A classical bit has two possible states, 0 and 1. You can think of it as a coin lying on a table. It's either heads or tails, that's all. Two states, two possibilities, pick one. A qubit also has two basis states, which we write as ket 0 and ket 1, using Dirac's notation. But a qubit can also exist in any combination of those two states, any weighted mixture of ket 0 and ket 1, where the weights are complex numbers. We write the state of a qubit as alpha times ket 0 plus beta times ket 1, where alpha and beta are complex numbers whose squared magnitudes add up to 1. Think about what that means mathematically. The state of a qubit is an ordered pair of complex numbers, alpha and beta, satisfying a normalization condition. It's a point on the surface of a sphere in 3 dimensions, the block sphere, which is the 3-dimensional version of the complex plane. A classical bit can only sit at the north pole, ket 0, or the south pole, ket 1. A qubit can sit anywhere on the surface. The entire sphere of possibilities is available. The smooth, continuous, infinitely divisible surface of a sphere, parameterized by complex numbers. Remember when we talked about complex numbers representing rotations?
On the block sphere, quantum operations are rotations. Applying a quantum gate to a qubit rotates the state vector to a new position on the sphere. And those rotations are described by matrices, specifically by 2x2 unitary matrices, exactly the kind that Cayley studied in the 1850s. So a qubit lives in a complex vector space. A quantum operation is a complex matrix. The probability of a measurement outcome is the squared magnitude of a complex coefficient, computed using the complex conjugate. Every single piece of the mathematical framework that we've traced from the 1500s to the present is operating here, simultaneously, in the definition of the simplest possible quantum computer, a single qubit with a single gate. Let me slow down here, because this is the part of the story where the abstract mathematics becomes a physical machine, and I want to make sure the picture is clear. A classical bit is the simplest possible piece of information. Yes or no. True or false. On or off. You can think of it as a light switch on a wall. It's either up or down. Those are the only options. And a classical computer, no matter how powerful, is just an enormous collection of light switches, flipping each other on and off in complicated patterns, very quickly. Now imagine a different kind of switch. Not the kind on a wall, but something more like a dial that can point in any direction on the surface of a sphere. It can point straight up, which we call ket 0. It can point straight down, which we call ket 1. But it can also point sideways, or at an angle, or anywhere on the surface. Every direction on the sphere represents a different quantum state, a different combination of ket 0 and ket 1. This sphere is called the Bloch sphere, named after the physicist Felix Bloch, and it's the standard way to visualize the state of a single qubit. At the North Pole, the qubit is definitely in the ket 0 state. At the South Pole, it's definitely in the ket 1 state. At the equator, it's in an equal superposition of both, a 50-50 chance of being measured as either 0 or 1. And between the pole and the equator, The superposition is unequal, leaning more toward one state or the other. But here's the thing about the block sphere that's subtle and important. The equator isn't just one state, it's a circle of states, all with the same 50-50 probability, but with different phases. Remember the complex plane? The phase is the angle of the complex number. Two states on the equator might both give you a 50% chance of measuring 0 and a 50% chance of measuring 1, but they differ in their phase, the relative angle between the complex amplitudes of ket 0 and ket 1. And that phase difference, which has no effect on the probabilities of a single measurement, has an enormous effect on what happens when qubits interact with each other, when they interfere. Think of it this way. Two qubits, both in a 50-50 superposition, might seem identical if you measure them individually. You'll get 0 half the time and 1 half the time from both of them. But if their phases are aligned in a particular way, and you bring them together through a CNOT gate, you get an entangled state. And if their phases are aligned differently, you get a completely different entangled state, or no entanglement at all. The phases are invisible individually, but they're decisive collectively. They're the hidden variables that choreograph the interference patterns that quantum algorithms depend on. And the gates, the operations you apply to qubits, are rotations on the block sphere. The Hadamard gate, which is probably the most used gate in quantum computing, takes a qubit at the North Pole and rotates it down to the equator, creating an equal superposition. Physically, if your qubit is a superconducting circuit, the Hadamard gate is a carefully timed microwave pulse that pushes the circuit into a state where the current is flowing in both directions at once. If your qubit is a trapped ion, it's a laser pulse that puts the ion into a superposition of two energy levels. If your qubit is a photon, it might be a beam splitter that gives the photon a 50-50 chance of going one way or the other. The physical implementations are different. The mathematics is identical. 2 by 2. 1 over root 2. 1, 1, 1, minus 1. That's the Hadamard matrix. It's the same matrix whether you're using superconductors, ions, or photons. The math doesn't care about the hardware. And when you apply a sequence of gates to a register of qubits, you're multiplying matrices together. The state of the register is a vector. Each gate is a matrix. The computation is a sequence of matrix multiplications applied to the vector. The final state is the product of all those matrices times the initial vector. And the output of the computation is obtained by measuring the final state, which collapses it, according to the Born rule, into one of the basis states, with probabilities determined by the squared magnitudes of the complex amplitudes. So a quantum computation is, mathematically, start with a vector, multiply it by a sequence of matrices, measure the result. That's it. That's the entire framework. And the reason it's more powerful than classical computation is that the vectors live in exponentially large spaces, and the matrices operate on all the dimensions of those spaces simultaneously. Let me give you a concrete sense of the exponential scaling. One qubit has a two-dimensional state space. 2 qubits have a 4-dimensional space. 3 qubits, 8 dimensions. 10 qubits, 1024 dimensions. 20 qubits, about 1 million dimensions. 30 qubits, about 1 billion dimensions.
50 qubits, about 1 quadrillion dimensions. 1024 qubits, more dimensions than there are atoms in the observable universe. Vastly more. Incomprehensibly more. This is the mathematical space that a quantum computer inhabits. And a quantum algorithm is a path through this space, a sequence of rotations that steers the state vector from a starting point to a destination where the amplitude of the correct answer is large and the amplitudes of the wrong answers are small. The art of quantum algorithm design is the art of finding these paths. And the tools of the art are the tools we've been tracing all night. Complex numbers, matrices, vector spaces, eigenvalues, Fourier transforms. Let me give you one more example of how elegantly the pieces fit together. Consider the Deutsch-Joja algorithm, which was one of the first quantum algorithms to demonstrate a provable speedup over classical computation.
It was proposed by David Deutsch and Richard Joza in 1992, and it solves the following problem. You're given a function that takes a string of n bits as input and returns a single bit, either 0 or 1. You're promised that the function is either constant, meaning it returns the same value for every input, or balanced, meaning it returns 0 for exactly half the inputs and 1 for the other half. Your task is to determine which case it is. On a classical computer, the worst case requires you to evaluate the function on just over half of all possible inputs, which is 2 to the n-1 plus 1 evaluations. For a function on 100 bits, that's an astronomically large number. On a quantum computer, the Deutsch-Joza algorithm determines the answer in a single evaluation, one query of the function. Here's how. You prepare a register of n qubits, all initialized to ket 0. You apply a Hadamard gate to each one, putting the entire register into a uniform superposition of all 2 to the n possible inputs. This is a single matrix operation, the tensor product of n Hadamard matrices applied to the state vector. Now the register is simultaneously in all possible input states, each with the same amplitude, 1 over the square root of 2 to the n. Then you apply the quantum version of the function. This maps each input in the superposition to its output. But because we're using the phase oracle trick, instead of writing the output to a separate register, the function's output is encoded as a phase flip on the input's amplitude. If the function returns 0 for a particular input, the amplitude is unchanged. If it returns 1, the amplitude gets multiplied by -1, a phase flip. Then you apply another round of Hadamard gates to the register, and here is where the interference happens. If the function is constant, all the phase flips are the same, either all positive or all negative, and the Hadamard gates rotate the state back to the all zeros state with certainty. When you measure, you get all zeros. If the function is balanced, half the amplitudes are positive and half are negative, and they interfere destructively, driving the all zeros amplitude to exactly 0. When you measure, you get anything except all zeros. One measurement, one query, constant or balanced, determined with certainty. And every step of this algorithm is a matrix operation on a complex vector space. The Hadamard gates are unitary matrices. The phase oracle is a diagonal matrix with entries of +1 and -1. The interference is the addition and cancellation of complex amplitudes. The measurement is the Born rule. The entire algorithm is a choreography of linear algebra, performed in a Hilbert space whose dimension grows exponentially with the number of qubits. This algorithm has no practical applications to speak of. The problem it solves is artificial, contrived specifically to demonstrate quantum speedup. But it illustrates, with crystalline clarity, the mechanism by which quantum computers achieve their power. Superposition puts the input into all states simultaneously. The function encodes information into the phases of the amplitudes. Interference amplifies the right answer and suppresses the wrong ones. And the mathematics of the whole process is complex linear algebra, the useless mathematics, working exactly as it was designed to work, 400 years after it was invented by people who had no idea what it would be used for. And when you have 2 qubits, the situation gets even richer. The state of 2 qubits together is not described by 2 separate vectors. It's described by a single vector in a 4-dimensional complex vector space.
which is constructed by taking what's called the tensor product of the two individual spaces.
This is the mathematical operation that takes a two-dimensional space and another two-dimensional space and combines them into a four-dimensional space. For 3 qubits, it's 8 dimensions. For 10, it's 1024. For n qubits, it's 2 to the n. This exponential growth of the state space is the fundamental source of quantum computing's power. A system of 50 qubits lives in a Hilbert space of more than 1,000,000 billion dimensions. Each dimension represents one possible combination of zeros and ones that the 50 qubits could be measured in. And a quantum computer, by manipulating a state vector in this vast space using carefully chosen unitary matrices, can explore all of those possibilities simultaneously. Not by trying each one in sequence, the way a classical computer would, but by following a single vector as it moves through a space that has room for all of them at once.
And the matrices that perform the manipulation, the quantum gates, are beautiful objects in their own right. The Hadamard gate, for instance, which is one of the most fundamental operations in quantum computing, takes a qubit that's in the ket 0 state and puts it into an equal superposition of ket 0 and ket 1. Its matrix is simply 1 over root 2 times the matrix with entries 1, 1, 1, minus 1. That's it. A 2 by 2 matrix with 4 numbers in it. And when you apply it, you rotate the state vector from the north pole of the Bloch sphere to the equator. From certainty to perfect uncertainty. From a definite 0 to a 50-50 chance of being measured as 0 or 1. The Pauli X gate, which is the quantum version of a NOT gate, flips ket 0 to ket 1 and vice versa. Its matrix is 0, 1, 1, 0. The Pauli Z gate leaves ket 0 alone, but flips the sign of ket 1, introducing a relative phase. Its matrix is 1, 0, 0, minus 1.
And the phase gate, the one that rotates the qubit around the z-axis of the Bloch sphere by an arbitrary angle, has entries 1, 0, 0, and e to the I theta, where theta is the angle. There it is again. Euler's formula, the complex exponential, the rotation in the complex plane. The mathematics of the 1700s, working away inside a quantum computer in the 21st century. For 2-qubit operations, the most important gate is the CNOT gate, the controlled NOT. This gate takes 2 qubits. The first is the control, and the second is the target. If the control qubit is in the ket 1 state, the CNOT flips the target. If the control is in ket 0, the target is left alone. In matrix form, it's a 4 by 4 matrix operating on the 4-dimensional tensor product space of the 2 qubits. And this gate, applied to certain initial states, creates entanglement. It produces states that cannot be factored back into the product of 2 individual qubit states. States where the 2 qubits become correlated in a way that has no classical analog. Entanglement is the phenomenon that Einstein called spooky action at a distance. It's the quantum mechanical fact that when 2 particles are entangled, measuring one of them instantaneously determines the state of the other, no matter how far apart they are. Einstein didn't like it. He thought it meant the theory was incomplete, but experiments, most famously those of Alain Aspect in the 1980s, and more recently the loophole-free Bell tests at Delft University in 2015, have confirmed that entanglement is real. Nature really works this way. And in quantum computing, entanglement is a resource. It's one of the things that makes quantum computers fundamentally more powerful than classical ones. An entangled state occupies a region of the vast Hilbert space that is inaccessible to any product state, any state that can be described by specifying each qubit independently.
The CNOT gate is the tool that opens the door to that region. And the CNOT gate is a unitary matrix operating on a tensor product of complex vector spaces. So here we are. A quantum computer is, mathematically, a system of vectors in a complex Hilbert space manipulated by unitary matrices, with measurement outcomes determined by the Born rule. Every word in that sentence traces back to a piece of abstract mathematics that was developed without any thought of practical application. The complex numbers from Cardano and Bombelli, the vector spaces from Hamilton and Grassmann, the unitary matrices from Cayley, the Hilbert spaces from Hilbert himself, the Bra-Ket notation from Dirac, the Born rule from Born, the exponential representation of complex numbers from Euler. Every piece, every last one. And this isn't just an elegant coincidence. The reason quantum computers are potentially so powerful is precisely that they operate natively in the mathematical space where quantum physics lives. A classical computer trying to simulate a quantum system has to translate that system's behavior into the language of bits, and the translation is lossy. It requires an exponential overhead. But a quantum computer doesn't translate. It computes directly in the space of complex vectors and unitary matrices. It speaks the native language. But speaking the language and saying something useful are two different things. Having a quantum computer, even a perfect one, doesn't automatically solve hard problems any faster than a classical computer. You need algorithms, carefully designed sequences of quantum gates that use superposition and entanglement and interference to guide the state vector toward the right answer with high probability. And finding those algorithms turned out to be extremely difficult.
For more than a decade after Deutsch's 1985 paper, people wondered whether quantum computers were just an elegant theoretical curiosity. And then, in 1994, a mathematician at Bell Labs in New Jersey changed everything. Peter Shor was not trying to change the world. He was working on a mathematical problem, the kind of thing that mathematicians at Bell Labs spent their days doing, deep in the quiet corridors of a research institution that had, over the decades, produced the transistor, the laser, information theory, and the cosmic microwave background radiation. Shor had a doctorate from MIT, a sharp mathematical mind, and an interest in computational complexity, the field that studies which problems are easy for computers and which ones are hard. And the problem he was thinking about was one that had been bugging computer scientists and number theorists for decades.
Given a large number, say a number with hundreds of digits, that is, the product of two prime numbers, can you find those prime factors efficiently? This might sound like a puzzle from a textbook, and in a sense, it is. But it's also the foundation of modern cryptographic security. A huge fraction of the encryption that protects your bank transactions, your email, your medical records, your government secrets, relies on a system called RSA, developed in the 1970s and named after its inventors, Rivest, Shamir, and Edelman. The security of RSA rests on a simple asymmetry. It's easy to multiply two large prime numbers together, but it's extraordinarily hard to do the reverse, to take the product and find the original factors. Easy to go one way, hard to go back. That's the trapdoor that makes RSA work. If you pick two prime numbers, each one say 300 digits long, and multiply them, your laptop can do this in a fraction of a second.
The result is a 600-digit number. But if you give someone that 600-digit number and ask them to find the two primes, the best classical algorithms known today would take longer than the age of the universe. Not because the algorithms are bad, because the problem is genuinely, fundamentally hard for classical computers. The number of operations required grows exponentially with the size of the number. And so the entire digital economy, the entire structure of secure communication, the entire architecture of internet trust, is built on the assumption that factoring large numbers is and will remain computationally infeasible. Shor broke that assumption. In 1994, he published an algorithm that could factor large numbers in polynomial time on a quantum computer. Polynomial time as opposed to exponential time. That's the difference between a task that takes a few hours as the number gets bigger and a task that takes longer than the universe has existed.
Shor's algorithm reduced factoring from practically impossible to routinely doable, at least in principle, given a sufficiently large quantum computer. The algorithm is a masterpiece of mathematical engineering, and it draws on every piece of the mathematical machinery we've been assembling. Let me walk you through the idea, not the full mathematical details, but enough to see why the useless mathematics is doing all the heavy lifting. The key insight behind Shor's algorithm is a connection between factoring and periodicity. Finding a period, a repeating pattern in a sequence of numbers, this connection comes from number theory, from the work of Euler and Gauss and other mathematicians of the 18th and 19th centuries who studied the properties of prime numbers and modular arithmetic. Here's the rough idea. Suppose you want to factor a number n. You pick a random number a that is less than n and shares no common factors with it. Then you look at the sequence a to the first power mod n, a squared mod n, a cubed mod n, and so on. Mod n means you divide by n and keep only the remainder. This sequence will eventually repeat. It has a period, a number r, such that a to the r mod n equals 1. Once you know r, there's a classical mathematical procedure involving the greatest common divisor that lets you extract the factors of n from r. The math is not trivial, but it's well understood, and it goes back to Euler. So the factoring problem reduces to the problem of finding the period r of this modular exponentiation sequence. On a classical computer, finding r is hard. You essentially have to compute the sequence term by term, checking whether you've hit a repeat yet. For large n, the period can be enormous, and the computation takes exponential time. But on a quantum computer, you can find the period efficiently, and the tool you use to do it is the quantum Fourier transform. The quantum Fourier transform is a quantum algorithm that converts information encoded in the amplitudes of a quantum state into information encoded in the phases. It's the quantum analog of the discrete Fourier transform, the mathematical tool that decomposes a signal into its constituent frequencies. You use it every time you listen to digital music, every time you make a phone call, every time your phone connects to a Wi-Fi network. The Fourier transform is everywhere in classical signal processing, and in quantum computing, it has a special property. On a classical computer, the discrete Fourier transform on n data points takes roughly n times log n operations, thanks to the famous fast Fourier transform algorithm. But on a quantum computer, the quantum Fourier transform on n amplitudes takes only about log squared n operations, exponentially faster. And the reason is that the quantum Fourier transform works by applying a cascade of controlled rotation gates, each one rotating a qubit by an angle that depends on the state of another qubit. And those rotations are implemented as 2 by 2 unitary matrices whose entries are complex exponentials. Euler's formula again. E to the I theta. The rotation in the complex plane that Euler discovered in the 1740s, embedded in the circuit that makes Shor's algorithm work. Here's how the pieces fit together. You prepare a register of qubits in superposition so that the register is simultaneously in all possible states from 0 to n-1. You compute the modular exponentiation function on this superimposed input, creating a quantum state that encodes the function values for all inputs at once. And then you apply the quantum Fourier transform, which extracts the period from the interference pattern of the quantum state. The phases of the complex amplitudes, the angles of the complex numbers that describe the state, encode the period.
and the quantum Fourier transform reads those phases off, converting them into a form that can be measured. When you measure the output, you get a number that is close to a multiple of n divided by r. From a few such measurements, you can deduce r, using a classical technique called continued fractions, which, beautifully, was also developed by Euler and his contemporaries in the 18th century. And from r, you get the factors. Every step of this algorithm, from the initial superposition to the modular exponentiation to the Fourier transform to the final measurement, relies on the mathematics of complex numbers and unitary matrices. The superposition is a vector in a complex Hilbert space. The modular exponentiation is a unitary operation. The Fourier transform is a product of controlled rotation matrices whose entries are complex exponentials.
The measurement is the Born rule, the squared magnitude of complex amplitudes.
Take away any piece of that mathematical foundation, the complex numbers, the matrices, the vector spaces, the exponential representation, and the algorithm collapses. It cannot work. Shor's algorithm sent a shockwave through the worlds of computer science, mathematics, and national security. Here was a theoretical demonstration that a quantum computer could solve a problem that no classical computer could solve efficiently. And that problem happened to be the one protecting the world's encrypted communications. The National Security Agency took notice. GCHQ in Britain took notice. Intelligence agencies around the world began paying attention to quantum computing research in a way they never had before. Now, it's important to say that in 1994, and for many years afterward, no quantum computer existed that could run Shor's algorithm on a number large enough to matter.
The largest number that has been factored by a quantum computer using Shor's algorithm, as of the time when these developments were being widely discussed, was 15. Into 3 and 5. That's not going to keep anyone at the NSA up at night. The quantum computers that existed were tiny, fragile, noisy, and prone to errors. Running Shor's algorithm on a cryptographically relevant number, a number with hundreds of digits, would require a quantum computer with millions of high-quality qubits and extremely low error rates. We are not there yet. We may not be there for a decade or more. But the theoretical result stands. The algorithm exists. The mathematics proves that it works. And the race to build a machine that can run it, or to develop new forms of encryption that are resistant to it, is one of the defining technological contests of the early 21st century. Shor's algorithm was not the only quantum algorithm that changed the game.
2 years later, in 1996, another researcher at Bell Labs, Love Grover, discovered a quantum algorithm for a different kind of problem: searching an unsorted database. If you have a list of n items, and you're looking for one that satisfies a particular condition, a classical computer has to check the items one by one. On average, it will take about n/2 checks. Grover's algorithm does it in roughly the square root of n steps. For a database with 1 million entries, that's 1,000 steps instead of 500,000. Grover's speedup is less dramatic than Shor's. It's a quadratic improvement rather than an exponential one. But it applies to a huge range of problems, essentially any problem that involves searching through a space of possibilities. And like Shor's algorithm, it works by manipulating amplitudes in a complex Hilbert space, using a technique called amplitude amplification. You start with a uniform superposition, apply an operation that marks the desired item by flipping the sign of its amplitude, a phase shift, and then apply another operation that amplifies the amplitude of the marked item relative to the others. Repeat this cycle about square root of n times, and the marked item's amplitude grows large enough that when you measure, you get the right answer with high probability. And once again, the operations are unitary matrices. The phase shift is a diagonal matrix with complex entries. The amplification step, called the Grover diffusion operator,
is a specific unitary matrix that can be decomposed into Hadamard gates and phase gates. The whole thing runs on complex linear algebra. After Shor and Grover, the field of quantum algorithms exploded. The engineering challenges are staggering. There's a reason that despite decades of theoretical development, quantum computers remain at an early stage. The fundamental problem is this: qubits are quantum objects, and quantum objects are exquisitely sensitive to their environment. Any interaction with the outside world, any stray photon, any vibration, any fluctuation in temperature or magnetic field can disrupt the delicate superposition that makes quantum computation possible. There are several competing physical technologies for implementing qubits. The superconducting qubits used by IBM and Google are tiny loops of superconducting metal cooled to near absolute zero, in which an electric current can flow in two directions simultaneously, forming a quantum superposition of current flowing clockwise and current flowing counterclockwise. Trapped ion qubits, developed by researchers including Christopher Monroe and Rainer Blatt, use individual atoms, ionized so they carry an electric charge, held in place by electromagnetic fields in a vacuum chamber. The qubit states correspond to different energy levels of the ion's electrons.
These systems can achieve very high fidelity, meaning very low error rates per gate operation. But they tend to be slower than superconducting systems. Photonic qubits use individual particles of light. Photonic quantum computers have the advantage that photons don't interact strongly with their environment, so decoherence is less of a problem. But they have their own challenges, including the difficulty of getting photons to interact with each other, which is necessary for 2-qubit gates. Topological qubits, the approach pursued by Microsoft, are based on exotic quantum states of matter that are intrinsically resistant to decoherence. The idea is that the quantum information is encoded not in the state of a single particle, but in the global topological properties of a system of particles, properties that are robust against local disturbances. This approach is theoretically beautiful, but technologically immature. As of the mid-2020s, the first topological qubits have only recently been demonstrated. Each of these approaches has its strengths and weaknesses, and nobody yet knows which one, or which combination, will ultimately prove most practical for building large-scale quantum computers. The race is genuinely open. What all approaches share is the underlying mathematical framework. Regardless of whether your qubits are superconducting circuits, trapped ions, photons, or topological excitations, the mathematical description is the same. Complex vectors in Hilbert spaces, unitary matrices, tensor products, and the Born rule. The physics is different in each case, but the mathematics is universal. The language doesn't change. And there's something worth noting about the scale of the challenge. A recent estimate suggested that to run Shor's algorithm on a number large enough to break RSA-2048, the standard encryption used in much of the world's secure communication, you would need a quantum computer with about 20 million physical qubits and the ability to execute billions of gate operations within the coherence time. Current quantum computers have a few thousand qubits at best, with coherence times measured in milliseconds and error rates of about 1 in 1,000 per gate. The gap is enormous. Closing it will require breakthroughs in hardware, in error correction, in compiler design, and in our fundamental understanding of quantum noise. And yet, progress is real. In 2019, Google's Sycamore processor, with 53 superconducting qubits, performed a specific computation in 200 seconds that Google estimated would take the fastest classical supercomputer about 10,000 years. The computation wasn't useful in any practical sense. It was designed specifically to demonstrate quantum advantage. But the demonstration was real, and it showed that quantum computers could, for the first time, do something that no classical computer could do in any reasonable amount of time. IBM has taken a different approach,
focusing on building increasingly large and reliable quantum systems and making them available to the public through the cloud. Since 2016, more than 3 trillion quantum computations have been submitted by users around the world through IBM's quantum platform. Most of these are small-scale experiments, but they represent a growing community of researchers, students, and enthusiasts learning to work with quantum hardware. The Chinese have invested heavily in quantum technology.
In 2020, a team led by Jianwei Pan demonstrated quantum advantage using a photonic system called Jiuzhang, which solved a sampling problem in minutes that would have taken a classical computer billions of years. China is also a leader in quantum communication, having launched the world's first quantum satellite, Misius, in 2016, and having built a quantum key distribution network stretching over 600 miles. And startups are proliferating. Companies like IonQ, Rigetti, Psi Quantum, and QEra are developing quantum hardware using various approaches, attracting billions of dollars in investment. The quantum computing industry, which barely existed 10 years ago, is now a global enterprise with government funding, corporate investment, and academic research programs spanning dozens of countries. All of this activity, all of this money and effort and ingenuity, is devoted to building machines that compute in the language of complex linear algebra.
Machines that manipulate vectors in Hilbert spaces using unitary matrices. Machines that harness the interference of complex amplitudes to solve problems that no classical computer can handle. Every qubit, every gate, every algorithm, every error correction scheme is built on the mathematical foundations that we've traced tonight. From Cardano's reluctant square roots through Euler's formula, through Heisenberg's matrices, through Dirac's notation. The mathematics that was once called imaginary, abstract, and pointless is the language of a global technological race that could reshape civilization. Researchers found quantum speed-ups for problems in optimization, in machine learning, in chemistry, in materials science. And in every case, the mathematical foundations were the same. Complex vector spaces, unitary matrices, tensor products, and the interference of complex amplitudes. The mathematics that Hardy had been so proud of having no applications turned out to be universal. It was the language in which every quantum algorithm was written, just as binary logic was the language in which every classical algorithm was written. So there was the theory, beautiful, powerful, mathematically airtight. Quantum algorithms could solve problems that no classical computer could touch. The mathematics worked on paper, the proofs were solid. And then came the part where you actually had to build the thing. Because the quantum world, the same world whose strangeness gives quantum computing its power, has a feature that makes quantum computation extraordinarily difficult in practice. The very sensitivity that allows a qubit to exist in superposition also makes it vulnerable to the faintest whisper from its environment. That vulnerability has a name. It's called decoherence, and it is the central engineering challenge of quantum computing. Decoherence is what happens when a quantum system interacts with its environment. When a qubit, which is supposed to be in a delicate superposition of ket 0 and ket 1, brushes up against a stray photon, or a vibration in the substrate it sits on, or a fluctuation in the magnetic field surrounding it, the superposition is disturbed. The complex amplitudes start to decay. The beautiful interference patterns that quantum algorithms depend on get washed out. The qubit, which was a quantum object living on the Bloch sphere, starts behaving like a classical object, collapsing toward the north or south pole. The quantum information leaks away into the environment, like heat leaking out of a poorly insulated house. And decoherence is fast. In the superconducting qubits that IBM and Google use, a qubit superposition typically lasts for about a millisecond before the environment overwhelms it. 1/1000th of a second. That's how long you have to set up your computation, perform all your gate operations, and read out the result before the quantum state dissolves. Every quantum gate takes a certain amount of time, and you're racing against the clock. This is why quantum computers are so physically exotic. The superconducting qubits used by IBM are cooled to about -459.6 degrees Fahrenheit, just a hair above absolute zero. That's colder than outer space, colder than any naturally occurring environment in the known universe. The entire apparatus is enclosed in layers of shielding to block electromagnetic noise, vibrations, even stray cosmic rays. The quantum processor itself, the chip that contains the qubits, is tiny, about the size of a fingernail. But the dilution refrigerator that keeps it cold is the size of a large chandelier, and the supporting electronics fill a room. And even with all of this isolation, decoherence still happens. Errors still accumulate. Every gate operation has a small probability of going wrong. And because quantum algorithms typically involve thousands or millions of gate operations, the errors add up. Without some way of correcting them, the computation is useless long before it finishes. This is where quantum error correction comes in, and it's one of the deepest and most mathematically beautiful parts of the entire field. The basic idea is counterintuitive. In classical computing, you can correct errors by making copies of your data. If a bit gets flipped by a cosmic ray, you check it against the backup copies and fix it. Simple. But in quantum computing, you can't copy a qubit. There is a theorem, the no-cloning theorem, proved in 1982, that says it is physically impossible to make an exact copy of an unknown quantum state. This follows directly from the linearity of quantum mechanics, from the fact that quantum operations are unitary matrices, which preserve lengths and angles. Copying is not a unitary operation. Nature forbids it.
So you can't make copies. You can't look at the qubit to check its state, because looking at it would collapse the superposition. How do you correct errors in a system you can't examine and can't duplicate? The answer, discovered by Peter Shor, yes, the same Peter Shor, in 1995, and independently by Andrew Steen in 1996, is to encode a single logical qubit across multiple physical qubits, in such a way that errors can be detected and corrected without ever learning the actual state of the logical qubit. It's like proofreading a document written in a language you don't understand, using only the rules of grammar. You can detect and fix typos without knowing what the document says. The mathematics of quantum error correction involves a beautiful interplay of linear algebra, group theory, and the theory of codes. The logical qubit state is a vector in a carefully chosen subspace of the larger Hilbert space of the physical qubits. Errors move the vector out of that subspace, and the error correction procedure projects it back in, using measurements that reveal which type of error occurred without revealing the state of the logical qubit. This is, I think, one of the most remarkable achievements in all of applied mathematics. A system that corrects errors in information it cannot read, stored in a form it cannot copy, using measurements that extract just enough information to fix the problem and not a bit more. And the whole thing is built on the mathematical framework of complex vector spaces, unitary matrices, and tensor products. Today, as of the mid-2020s, quantum computers are real. They exist. You can access them over the internet. IBM has quantum systems with over 1,000 qubits, accessible through the cloud, and anyone can submit a quantum algorithm and have it run on actual quantum hardware. But we are still in the early days. The qubits we have are noisy. The error rates are too high for most practical algorithms. Running Shor's algorithm on a number large enough to break RSA encryption is still far beyond current capabilities. The quantum computers we have today are sometimes compared to the classical computers of the 1950s, room-sized machines that could do less computation than a modern pocket calculator, but that pointed unmistakably toward a revolution. And the path from here to there, from the noisy intermediate-scale quantum computers of today
to the fault-tolerant, error-corrected quantum computers of the future is a path that runs through mathematics. Through better error-correcting codes, which are algebraic structures, through more efficient quantum algorithms, which are sequences of unitary matrices, through deeper understanding of decoherence, which is described by the theory of open quantum systems and completely positive maps, through the design of quantum hardware, which requires solving Schrödinger's equation for complex superconducting circuits. The useless mathematics is doing all of it, every piece of it, right now, in laboratories around the world, in the code that researchers write, in the papers they publish, in the grants they apply for, in the chips they design. The mathematics that Cardano called as subtle as it is useless is the language in which the future is being written. And the future is not just about faster factoring or better database searches. The applications that most experts believe will be the first to show genuine quantum advantage are in simulation, exactly as Feynman predicted in 1981. Simulating molecules, designing new drugs, understanding chemical reactions, discovering new materials. When a pharmaceutical company wants to understand how a drug molecule interacts with a receptor in your body, the interaction is quantum mechanical. The electrons in the drug and the electrons in the receptor are quantum objects, governed by Schrödinger's equation, living in complex Hilbert spaces, obeying the rules of unitary evolution. A classical computer has to approximate this behavior, and the approximation is often crude, expensive, and slow. A quantum computer could simulate it directly, in its native mathematical language, without approximation. This is the deep promise of quantum computing. Not that it makes everything faster, it doesn't. Not that it replaces classical computers, it won't. But that it gives us access to a realm of computation that is native to the mathematical structure of the universe itself. A realm where complex numbers and unitary matrices and tensor products are not abstractions, but physical reality. A realm where the imaginary part of mathematics is, in the most literal possible sense, real. And that brings us back, finally, to the question we asked at the beginning of tonight.
Is mathematics something we invent, or something we discover? And here is where the road forks, and we stand for a moment, looking both ways. In one direction lies the engineering future, the path of more qubits, lower error rates, better algorithms, faster coherence times, the long march toward a fully fault-tolerant quantum computer, capable of simulating molecules, optimizing logistics, cracking codes, and doing things we haven't yet imagined. That path is uncertain, difficult, and potentially transformative on a civilizational scale. Michio Kaku has compared the current moment to the early days of the transistor revolution, when the devices were crude and the applications were speculative, but the trajectory was unmistakable. We're entering what he calls the fourth great era of scientific innovation, after steam, electricity, and the transistor. And whether that comparison proves justified or optimistic, the fact remains that governments, corporations, and researchers around the world are betting heavily on it. In the other direction lies a philosophical question that has no engineering answer, and may never have one. The question of why the universe is described by this mathematics. Why complex numbers? Why matrices? Why Hilbert spaces? Why should the physical world, at its most fundamental level, speak a language that was invented or discovered by mathematicians following their own curiosity, often centuries before the physics needed it? Neil deGrasse Tyson, in his discussions with Kaku about quantum computing, made a point that resonates here. He pointed out that in 1925, the people probing atoms and developing quantum theory could easily have been dismissed as irrelevant dreamers. The world was in the grip of economic hardship. People were hungry. And here were these physicists, tinkering with the insides of atoms, asking questions that seem to have no connection to the practical needs of society. If you had stopped them, if you had defunded their research, if you had told them to do something useful, then the transistor would never have been invented. The integrated circuit would never have been developed. The computer revolution would never have happened. The smartphone in your pocket would not exist. The entire digital infrastructure of modern civilization traces back to the work of people who were studying atoms for no reason other than curiosity. And the same is true, Tyson argued, of quantum computing today. The researchers building qubits and designing quantum algorithms are the intellectual descendants of those atom probers of the 1920s. Their work may seem abstruse, impractical, remote from everyday concerns.
But the pattern of history suggests that this is precisely the kind of work that transforms the world in ways that cannot be predicted by the people doing it, on timescales that are longer than a quarterly earnings report, but shorter than a human lifetime. The history of quantum computing is, at its deepest level, the history of pure curiosity. Curiosity about numbers that don't exist. Curiosity about tables of numbers that don't commute. Curiosity about wave functions that take complex values. Curiosity about what happens when you try to simulate nature on a computer. Curiosity about how to factor large numbers. Curiosity, followed wherever it leads, regardless of whether anyone can see a practical application. And tonight, as you drift towards sleep, that's maybe the most comforting thought of all. That the story we've traced, from Cardano's Italy to Shor's New Jersey, from the square root of -1 to the quantum Fourier transform, is a story about the power of curiosity,
about the unreasonable, unpredictable, and ultimately indispensable usefulness of following a question simply because it's interesting. About the deep structure of a universe that, for reasons no one fully understands, rewards the explorers who go looking for beauty in abstraction with the tools to build the future. Gerolamo Cardano, in 1545, was trying to solve a polynomial equation. He didn't want to discover the square root of -1. He wanted it to go away. But it wouldn't. And 480 years later, it's the heartbeat of a technology that might reshape civilization. The story we've walked through tonight is, in a sense, a single story told in 2 acts. The first act is the creation of a mathematical language, a language that was built piece by piece over centuries by people who were following their curiosity, solving puzzles, exploring structures that interested them. Cardano and Bombelli with their impossible numbers.
Euler with his astonishing formula connecting exponentials and trigonometry and the imaginary unit. Gauss and Argand with their picture of complex numbers as points in a plane. Hamilton with his quaternions, carved into a bridge in Dublin, non-commutative and strange. Cayley with his matrices, rectangular tables of numbers that could describe transformations in space. Hilbert with his infinite dimensional vector spaces, each one adding a piece to a structure that nobody knew would be needed. The second act is the discovery that the universe already spoke this language, that when physics reached deep enough into the structure of matter, when it probed atoms and electrons and photons, when it tried to describe the behavior of the very small, the only language that worked was the one that the mathematicians had built. Complex numbers at the heart of the wave function, non-commuting matrices at the heart of the uncertainty principle, unitary transformations at the heart of quantum evolution. Hilbert spaces as the stage on which all quantum phenomena play out. And quantum computing is the moment where the 2 acts merge, where we take the mathematical language of the universe and turn it into a technology.
where we build machines that compute directly in the native tongue of nature, using the same complex vector spaces and unitary matrices that describe the behavior of every atom and every photon. The physicist Eugene Wigner, in a famous essay from 1960, called this the unreasonable effectiveness of mathematics in the natural sciences. He was puzzled by the fact that mathematical concepts developed for purely abstract reasons kept turning up in physics. Why should the complex numbers, invented to solve cubic equations, be necessary for describing quantum mechanics? Why should the matrices, invented to study abstract transformations, be the right framework for describing atomic spectra?
Why should the geometry of Hilbert spaces, developed by mathematicians exploring infinite dimensional generalizations of Euclidean space, be the exact structure needed for quantum theory? Wigner didn't have an answer. Nobody does, really. It's one of those deep questions that sits at the intersection of mathematics, physics, and philosophy, and that may never have a fully satisfying resolution. But the fact itself is undeniable. Mathematics that was developed without any thought of application turned out to be indispensable for understanding the deepest laws of nature. And now it's indispensable for building the most advanced technology our species has ever attempted. There's a passage in Brian Cox's discussions of quantum mechanics where he talks about complex numbers as little clock faces, following Feynman's description. Each complex number has a hand, like a clock, and a length, like the hand's size. When a particle travels from one point to another, you assign a little clock face to every possible path it could take. At the destination, you add up all the clock faces, letting the hands point in their different directions and cancel or reinforce each other. The length of the final hand gives you the probability of the particle arriving there. That's it. That's quantum mechanics. Little clock faces, which are complex numbers, adding up according to the rules that Argand and Gauss and Euler worked out centuries ago. And in a quantum computer, the qubits are clock faces too. Each one has a magnitude and a phase. The gates rotate the hands. The algorithms are choreographies of rotations, carefully designed so that the wrong answer's clock faces cancel each other out. Destructive interference. While the right answer's clock faces all point in the same direction. Constructive interference.
When you measure, the amplitude of the right answer is large, and you get it with high probability. The magic of quantum computing is interference, and interference is nothing more than the addition of complex numbers. So quantum computing is, in its deepest essence, the art of orchestrating complex numbers. The art of arranging rotations in a vast, multidimensional, complex space so that the wrong answers cancel and the right answers survive. And every tool used in that orchestration, every gate, every algorithm, every error-correcting code, speaks the language that Cardano discovered and hated, that Euler formalized and loved, that Heisenberg reinvented without knowing, that Dirac abstracted into elegance, and that Peter Shor wielded to crack the foundations of modern cryptography. There is something profoundly moving about this, if you let yourself feel it.
The idea that a mathematical accident, a number that was forced into existence by the demands of an equation, an unwanted guest at the party of arithmetic, could turn out to be, 5 centuries later, the key to the most powerful computational technology ever imagined. The idea that pure curiosity, the kind of curiosity that makes a person spend 10 years trying to extend the number system into 4 dimensions, or a lifetime developing the theory of infinite dimensional vector spaces, that this kind of curiosity pays off in ways that are utterly unpredictable, and yet, in hindsight, feel almost inevitable. Tonight, wherever you are, the mathematics is at work. In the Wi-Fi signal that carried the last thing you looked at on your phone, in the encryption that protects your most private data, in the transistors that process every digital thought your devices have, in the quantum computers humming in their dilution refrigerators in Yorktown Heights and Zurich and Sydney, cooled to 15,000ths of a degree above absolute zero, manipulating states in complex Hilbert spaces using unitary matrices, running algorithms that depend on the interference of complex amplitudes. And in you, because you are made of atoms, and atoms are quantum objects, and the behavior of quantum objects is described by complex-valued wave functions evolving according to Schrödinger's equation, which is built around the Hamiltonian that Hamilton invented, using the complex numbers that Cardano discovered in the Hilbert space that Hilbert defined. Your body right now is a quantum system. The electrons in your cells are distributed in probability clouds described by complex-valued orbitals. The chemical bonds holding your molecules together are quantum mechanical, governed by the exchange of electrons in overlapping complex wave functions.
The photons that your retina absorbs are quantum particles, each one a discrete packet of energy carrying a phase, a complex number, an angle on a little clock face. The mathematics that was considered useless is the mathematics that describes you. And right now, as you lie here, your body is doing what it does every night. Your brain is winding down. Your neurons are beginning the slow transition from the high-frequency firing patterns of waking consciousness to the long, rolling delta waves of deep sleep. The neurotransmitters that kept you alert during the day are ebbing, and the ones that promote sleep are rising. Adenosine is accumulating in your synapses, the molecular signal of tiredness. Melatonin is circulating, the hormone that your pineal gland releases in response to darkness. All of these processes are, at the deepest level, quantum mechanical. The neurotransmitters are molecules, and molecules are quantum objects. The ions flowing through your nerve cell membranes, the sodium and potassium that generate the electrical signals of thought, they obey quantum mechanics. The photoreceptors in your retina that detected the light of your screen, each one was triggered by a single photon, a quantum of electromagnetic energy. Your consciousness, whatever it ultimately turns out to be, runs on hardware that is quantum mechanical from the bottom up. So you are, in a very literal and precise sense, a quantum computer, an astonishingly complex one, with something like 86 billion neurons and 100 trillion synaptic connections, running on chemical reactions that are quantum mechanical in nature. The difference between you and the quantum computers in the laboratory is that your quantum processes are warm and wet and messy and robust, shaped by billions of years of evolution to work reliably in the noisy environment of a living body.
The quantum computers in the laboratory are cold and clean and fragile and new, designed by engineers who are, in a sense, trying to learn from nature how to harness the same underlying physics. But the mathematics is the same: the complex numbers, the vector spaces, the unitary transformations, the interference of amplitudes, the Born rule. It's all the same mathematics, the mathematics that Cardano stumbled onto, that Bombelli systematized, that Euler connected to geometry, that Heisenberg rediscovered on a windswept island, that Schrödinger embedded in a wave equation, that Dirac abstracted into a notation, that Shor turned into an algorithm. It's all one story. One long, winding, improbable, beautiful story about a species that invented a language, not knowing it was the language the universe already spoke. And tonight, the universe is speaking it in you. In the quantum processes of your neurons, in the photons that are no longer hitting your retina because your eyes have closed, in the electrons settling into their lowest energy orbitals as your metabolism slows. The complex amplitudes are evolving. The wave functions are doing their thing. The mathematics is running, quietly, reliably, in the dark. You don't need to hold any of it in your mind. The equations will still be there in the morning. Cardano's reluctant square roots, Euler's perfect formula, Hamilton's bridge, Heisenberg's island, Schrödinger's wave, Dirac's elegant brackets, Shor's algorithm. They're part of the story now, part of the long human adventure of figuring out what the universe is made of and how it computes. And the most remarkable thing, the thought I want you to carry into sleep, is this. Every one of those discoveries was made by someone who didn't know where it would lead. Cardano didn't know he was laying the foundation for quantum computing. Euler didn't know his formula would describe the rotation of qubits. Hamilton didn't know that non-commutativity would be the defining feature of the quantum world. Heisenberg didn't know that the tables of numbers he was multiplying were matrices. Each of them followed their curiosity, pursued a question because it interested them, and trusted that understanding was worth having for its own sake. And each of them, without intending to, without imagining it, built a piece of the future. That's what pure curiosity does. It builds things you can't predict. It answers questions that haven't been asked yet. It creates tools for problems that don't exist yet. And when the problems finally arrive, the tools are there, waiting, as if they'd always known they would be needed. So let that settle. Let the numbers drift. Let the complex amplitudes do their quiet work in the background, the way they always do, the way they've been doing since long before anyone was around to notice. The universe is computing.
It's been computing for 14 billion years, in the language of complex numbers and unitary matrices, in every atom and every photon and every interaction. And you are part of that computation. A brief, remarkable, conscious part. A part that, tonight, knows a little more about the language than it did before. Let your breathing slow. Let the ideas soften. Let the history and the physics and the mathematics blur at the edges, the way a landscape blurs when you look at it through half-closed eyes. Cardano's Italy, Euler's Switzerland, Hamilton's Dublin, Heisenberg's Ireland, Shor's New Jersey. They're all distant now, part of the long past, connected by a thread of equations that runs through all of them and through you. The math is solid. The logic holds. The qubits, wherever they are tonight, are being kept cold and quiet and still, and the engineers who watch over them are doing their careful, patient work, making sure the amplitudes stay coherent for just a little longer, for one more gate operation, one more step toward the future. Let them do their work. Let the universe do its work. Let your body do its work, the ancient, reliable, quantum mechanical work of resting and restoring. Everything is still here. The complex numbers, the matrices, the vectors, the phases, the interference, the whole beautiful, improbable mathematical structure that nobody expected and nobody can quite explain, but that holds the universe together, from the inside of an atom to the inside of a quantum computer to the inside of you. Just breathe. The math will keep.